I actually built some. So the first part of this presentation exposes the secrets of this phenomenal machine. I would like to acknowledge Glenn A. Robertson, my associate, who was instrumental in the final development and testing of the drive we are presenting today. I hope you enjoy our presentation. I thought I did. I thought I could build some. For every action, there is an equal and opposite reaction, but not immediately. Taking advantage of inertial delay. Breaking centrifugal force from rotary motion for propulsion has eluded us humans for millennia. The hurdle, it seems, lay in the way we tend to think about our world at large. In the past, we inventors and engineers generally thought in terms of how to lasso the rotor by manipulating a spinning mass on a stationary scaffold. The quest is, and always was, to generate unidirectional force from rotary motion. Yet few of us consider giving the scaffold free range in the corral to harness the rotor. Furthermore, knowing how to do something may not be as important as knowing when to do it. Norman L. Dean found that elusive answer by manipulating time within the cycle of a spinning rotor. But first, we had to convert the rotary motion into oscillations. You can use any eccentric rotor and rectify it to get an unbalanced force simply by diddling with the pace of T. Manipulating time? How is that even possible? Let's say your deranged uncle died and left you with 1,000 used cars, and they were just delivered into your backyard. You drive one car for a mile to a dealer, haggle for a bit, and sell for pure profit, but you have to walk back home. You drive another car to the same dealer, haggle, and sell again for a profit, and then walk back home. You repeat the cycle until you've sold all of your cars. By then you have enough money to move into a new home. This is how a Dean drive works. Your car lot may be likened to a source of electricity. You are the eccentric rotor in a Dean drive that is shifted when you save time by driving to the dealer. To your neighbor who is not quite certain that you either A, desert the rubber room at the Winfield Hotel, B, wash the Q-tip, C, put one on the coconut for the team, D, not sleep dog ashtray. From your neighbor's perspective, though, your cycle of driving away a car and walking back remains constant. But to you, time is saved driving to the dealer. You spend that extra time in haggling out a profit. You then spend an equal amount of time you did in driving and haggling on the return walk back home. Externally, the system appears balanced. Internally, it's unbalanced. It's a question of different inertial frames of reference. Likewise, Dean drives convert energy from electricity cars into rotary motion round trip, and then into an oscillatory action repeated round trips. The shifting of the rotor with drive, the clutching of the rotor, the haggling, to create centrifugal force profit. The walk back home is within new space. So how did Dean change the pace of time in a machine? Norman Dean's patent 2886976 of his electromechanical inertial drive has intrigued millions for a better part of a century. So why hasn't someone built a flying machine based on its principle by now? The problem, as it turned out, were patent rights protection. Dean laid out his art so skillfully that without extensive research, even the most clever engineer could not duplicate all the variables. For example, what are and how do you harmonize the proper shift timing, clutch timing, stroke length, system amplitude, rotor mass, spring tensions, and the placement of slider switches? But was the Dean drive for real? Despite these hurdles, obviously the system worked because in the 1960s, there were many credible witnesses, including the late William O. Davis. Dr. Davis, who worked for the US Air Force at the time, was so convinced that he calculated Dean drives could exist in the universe. Davis even went so far as to propose an addendum to Newton's laws of motion, a fourth law. The energy of a given system can only be changed in some finite length of time, depending on the system, and never in zero time. The conservation laws of energy and momentum are upheld because the power demands are periodic. Inertial frames. Davis coined the term critical action time, or CAT, used to define the period when a mass is subjected to a force and when it begins to react to that force. Because there are gaps between action and reaction, there can be separate inertial frames in a machine. Within Dean drives, we can witness three inertial frameworks at play. One, the rotors and their angular momentum driving the carriage. Two, the carriage itself as it oscillates with the rotors. Three, the main frame load that houses the above complex. Dr. Davis's theoretical model of a unidirectional impulse drive or unbalanced oscillator. A, the oscillator. Sine wave or sawtooth waveform may be critical. A is also what we call the carriage. B, long time signal path. C, short time signal path. D, clutch, timing is critical. E is clutch. F is a frame load. Impulse direction is towards the left. Making of a Dean drive. Step 1, build the oscillator by channeling rotary motion. To do this, suspend the rotor axle, creating a second inertial frame within the system. Step 2, counterspinning weights mounted on a suspended second inertial frame or carriage will propel that carriage bidirectionally when both rotors swing to either side of said carriage. This is a balanced mechanical oscillator. Note, forces generated by the eccentric rotors when their armatures are in line with actual conjunction are canceled out. Conveniently, cancellation and addition forces hold true for both horizontal and vertical carriage systems. Fine, but now we have a problem. One would logically predict the carriage to swing in the opposite direction of the rotors, right? Nope. A fundamental anomaly. The resultant mechanical oscillator is a balanced system. It converts 360-degree rotary motion into a powerful 180-degree bidirectional force. Why does the carriage swing with the rotors instead of away, as would be predicted by Newton's third law? The reason: since the rotors are counter-spinning, side forces are canceled out, and the carriage swings towards the sum of the rotor's angular momentum, demonstrating centrifugal force can be isolated from the centripetal. Step 3, rectify it. Next, we take advantage of low rotor inertia to shift the axis of the eccentrics to make an unbalanced mechanical oscillator. This occurs at a precise time in the cycle when the rotors are approaching zero line between negative and positive phase. The genius is in the timing. We take advantage of the rotor's reduced inertia when their armatures align, R to R. And the rotor's inertia are negligible because they are moving in the right direction, making the system extremely efficient. In shifting the rotor's axles, we decrease the cat of the system in positive phase to release repetitive centrifugal surge accelerations. These forces are then applied to the third initial frame, the housing of the engine with its load. Okay, awesome. We have a rectified mechanical oscillator and a putt puts along like a pissed off squirrel in a shoebox. But wait. Something doesn't look right. The rotors are making elliptical patterns that are tilted. The ellipse on the left is a classical notion of how a rotor appears when subjected to a bilinear motion. The ellipse on the right represents the described pattern of what actually occurs under these conditions. Okay, plane of oscillation is left to right, right to left. Phenomena of phasing in Dean rotors. This is because the rotors are driving the carriage 45 degrees ahead of themselves. This too is not predicted in classical mechanics. So timing of the shift must take this 45-degree phase lag into consideration. This is one of the major stumbling blocks for engineers trying to get a Dean drive to work. Surge, a third form of motion. Obviously, in Dean drives, the classic notion of spinning rotors on an oscillating axle does not hold true. In reality, such a rotor can have as much as 135-degree separation between its velocity and acceleration vectors instead of the usual 90 degrees we see in rotary motion. 135 degrees. So 90 degrees plus 45. Third derivative effects. Furthermore, when subjected to a linear shifting action, the rotor produces far more force than what could be predicted in classical mechanics. The Davis arc appears to be where this mythical inertial radiation or virtual energy, postulated by Davis, originates from the eccentric Dean drive rotor. Improving on the Dean drive. In the 1950s, Norman Dean did not have the luxury of a huge variety of spring types and rates to experiment with. Nor did he have digital electronics or access to compact and powerful electric motors. In fact, the motors used on our engines were built in the late 1980s, and though of high quality Japanese engineering, they do not use rare earth magnets. Recent designs and motor technology would make our engines even more lighter and powerful. Our other contributions to the Dean drive at this juncture have been in the dampening of the carriage recoil
shortening the recovery time. We also incorporated an electronic commutator and consolidation of all machine components. Most importantly, we reconfigured the suspension system. Let's glance at some of the steps we've taken to arrive at a practical impulse drive. This is engine E2 with its power supply E1. Engine E3, that is not a Dean drive. This one, the first one is a Buehler drive. The second, third engine E3 is a radial vector drive. It's not a Dean drive. This is power supply PS2. This is engine E6 with a cover box and load sled. And this weird looking little engine is engine E9, little Hermann Munster mobile. It uses a rod, a rack and pinion rod to impact with an asymmetrical oscillator, marginal thrust. This is a 2-cycle Dean drive, engine E8, that's patent drawing. We had issues with getting the carriages to synchronize or desynchronize so that we'd get thrust out of it. This is engine E5, a 4-cycle drive. It too has issues with desynchronization. And here's E5 on its back. Of all the engines I've built, few had the force needed to propel us in space, but my single-cycle Dean drive showed the most promise. So I had to go back to the beginning to review and reset parameters. Inertial engine E4. I built my first Dean drive in 1992 and tried to stay true to Norman L. Dean's first patent. It is a junk box jalopy made from whatever parts I could find. Dr. Tom Valone was the first physicist to witness its operation back in 1995. It can be viewed in operation on my first YouTube video. 5.4 pounds, ounces, rotors are 4.6 ounces times 2. Rotors require 17 watts of power, shifter 19 watts, total 36 watts to operate. Power supply PS3. Dean drives require 2 separate voltages. I built this custom dual DC power supply for engine E4 in 1992. Then beefed it up in 1996 for other engines. PS3 delivers upwards of 300 watts if needed. Inertial engine E6, I built this second modified Dean drive in 1995. E13, the engine that we will be demonstrating today, the asymmetric impulse drive, is an upscaled version of this drive, but with many new innovations. Engine E6 may be viewed on my third YouTube video. This is a single voltage engine, variable speed, 2.6 pounds. Rotors are 4.4 ounces together, 13 watts average. Power supply PS5. Dean drives are extremely efficient. As it turned out, I needed a power supply that I could easily move about that didn't promise to Frankenstein me with 10 amps of DC current on the damp basement floor of my earlier laboratory. So I built the lower wattage PS5. Asymmetric impulse drive. Engine weight, 8.7 pounds. Would have been 7.7 pounds if I could have gotten some threaded aluminum rods. Here I used brass, which support rods, which increase the weight of the engine by an extra pound. Unlike my other drives, this engine was designed to be adjustable in all facets, but I had to go back to a dual voltage power source, PS5, one fixed for the shifter, and a variable for the motor so I could fine-tune rotor speed. This simple erector set design allows us to adjust shifter stroke length, to establish carriage amplitude, to choose various spring rates, easy access to all parts, ease of assembly and adjustments in repair, can be easily upscaled. Here we have a couple of my patent drawings. Dean and Davis were right. Before the mainframe can react to the impulse from the carriage is already recovering its position during that initial delay of the mainframe's mass load. This can be witnessed in slow-mo in our latest YouTube video that we will see shortly. Like the kid on the playground swing, a 10-degree tilted pendulum offers the least resistance to the drive under test. Excellent efficiency. Shifter, 25% duty cycle only requires 10 watts. Rotors, about 8 watts. Total power consumption around 18 watts average to get 14 to 20 pounds impulse, which comes out to about 1 watt to 1 pound of force. I think I know this one. This was our first accelerometer test. G-force came out to be around 1.6 G average. Engine was free hanging. This was our earlier load cell test. Engine secured to the bench through the load cell down here. Bolted to this plate, which is anchored with a pony vise and clamped down to the bench. And the engine is free hanging, but it can't swing. It's bolted to the bench. And we were getting about 20 pounds of impulse at close to four cycles per second, 4 hertz. This is a testing apparatus devised by Glenn used for the next set of experiments. Okay, this is the G-force. We use the physics lab assistant accelerometer test program. As you can see, the green trace goes up past 2 Gs. Now, remember this trace form, because you will see it again under a load cell test. And this is very interesting. We're going to take a close look at the load cell trace form, which is very similar to this pattern. Again, this engine was free hanging. Again, this is for 1 cycle with a duration of 440 milliseconds. Now we reduced the rotor voltage to 8 volts DC for uniform clarity so that we could see the wave pattern. Note the near identical tracking of the waveform pattern in the next slide, also 1 cycle, same duration. Here's a load cell test. Upwards of 13.5 pounds of force. We actually have 4 positive pulses in 1 cycle here. And I will explain that to you. It's very interesting. Okay, short time signal path, the ride. Cycle starts at Mach 300. Actually, the cycle starts here. Starting from carriage mid-range, R to R, the rotors drive the carriage forward while the solenoid fires, advancing the carriage and gaining cat. The rotors then impart acceleration to the mainframe during that 100 milliseconds with 5 pounds force, which is about 22% of the cycle. So here, the solenoid is activated, pulls the carriage forward while the rotors are also going in the same direction. There's 5 pounds of force. Long time signal path, the walk back home. At 400 milliseconds, the solenoid releases and the carriage rapidly retreats to negative phase with a slight ringing of 50 milliseconds. Okay, carriage releases, there's a ringing of the engine, slight. And a residual pulse of 50 milliseconds with 2 pounds force. There's another pulse at 2 pounds. This inertial lag of 100 milliseconds accounts for another 22% of the cycle. The cycle continues at Mach 65 milliseconds. So the cycle continues here. The rotor carriage complex reaches peak negative phase when the first large positive spike manifests on the mainframe with 13.5 pounds of force. Okay, the carriage is already towards the back of the mainframe when this pulse occurs. This 25 millisecond spike is the mainframe's delayed reaction to the solenoid firing. Then the mainframe reacts according to Newton's third law and gives a short negative recoil spike of 15 milliseconds. Recoil spike. This 40 millisecond event accounts for 9% of the cycle. Now this gets interesting. From 100 milliseconds to 300 milliseconds, 100 milliseconds to 300 milliseconds. The mainframe is now reacting to a large phantom pulse of 60 milliseconds with 8 pounds impulse from the rotor centrifugal force, Davis's virtual energy, delayed reaction. Carriage is nowhere near the front end of the engine, the mainframe. You can see the carriage dampening effect in this pulse, after which the carriage is free to finish dampening for another 140 milliseconds, settling into RR mid-range. So here's the carriage. It's trying to dampen out, but that pulse is there. And then the pulse is gone and the carriage is dampening out, getting ready to start another cycle. This phenomenon is 200 milliseconds and accounts for 47% of the cycle. So as you see here, in one cycle, we have 4 positive pulses. Here's Glenn and I's contact information. Well, I hope you enjoyed our presentation. And Glenn and I are both looking forward to hearing from you. Thank you. In the translation test, we have the engine on roller bearing wheels set on level rails. Watch as the carriage does its heartbeat rhythm between its long and short time signal path. We run the engine in both directions to show that the rails are level. Next will be the water boat test. The pendulum test is the gold standard for testing inertial type drives. There is a general expectation that a drive under the pendulum test needs to hover to one side of zenith to be a viable source of propulsion. This is not true, as our accelerometer and load cell tests prove out. With our present technology, any impulse drive that has respectable force will be a low frequency device and settle back between each pulse on the pendulum because of gravity. Here, we have the engine hanging from pendulum lines where it can swing freely. We have found that a level machine hanging from a pendulum cannot move quite so freely because it has to lift itself up slightly to displace its position. We are testing for unidirectional force, not multidimensional force. For example, when we kick up our feet to gain altitude on the playground swing, we are following the natural arc of the swing. The same applies here. This is why we have a 10-degree upward tilt of the engine. I will start the engine now. The direction of force is to the right. For those of you who do not agree with me on the tilt issue, we will run the engine level. One can see that E13 wants to go places. Note the machine wants to leap forward with each pulse. As we have seen on the load cell chart, this force is quite substantial.
Myself, not hearing. So we have concluded Steve Hampton's presentation, and we're in between the performances and presentations. Currently, we don't see any questions that have popped up in the chat window for Steve. But if you have any, certainly you can post them there. But Steve's contact information was also provided and in his slide presentation. I also sent everyone the link to the COFE program PDF if you would like to download that or open it and read in sequence what we're doing today and tomorrow up through 6 p.m. You can do that, and it's all in color. It has pictures of everyone and nice biographies and abstracts as well. So feel free to look at the chat window for information. And the contact information for Steve Hampton, let me see if I can pull that up since there was a question about that, and we'll make that available in the window right now if I can. Let's see. Okay, your conversion down to the end of his presentation. And yes, there we go. Okay, so let me share the window and then share screen, and I can leave that to let you copy down his contact information. Okay, so you should still be hearing me, but now you're looking at contact information for Glenn Robertson, who has been his technical consultant for all the analytical information that you heard about, and also the simulations they did as well, which was very valuable. And then Steve Hampton's email, and also inertialpropulsion.com, which is a great website. I'm glad he grabbed that URL since it applies to over 100 patents that our institute actually provides. If you're interested, if you go to integrityresearchinstitute.org, you can actually order reports on inertial propulsion. And the 100 patent collection is a great resource and a reference for those who are studying this science, which today you'll be treated to a second performance for presentation at 2 p.m. Eastern Time by Mike Gamble, who has experience from Boeing in inertial propulsion devices that they built. So I know the history of this. It's been very fascinating with people back in the 1980s, Robert Cook and Roy Thorsten and others, that impressed Boeing enough to be able to let them build their own proprietary version. And now Mike Gamble has retired from Boeing with all the information that he took with him. So between Steve Hampton and Mike Gamble, hopefully we'll see one of these on the market soon, so we can have electric propulsion. And electric propulsion is greatly improving the fossil fuel problem that we currently have. Obviously, with any transportation, land, air, or in the sea, or in the air, or in space, they all seem to burn fuels to get to where they're going. And this is the only hope for, probably one of the only hopes, besides electrolytics, to see that the future could be a clean energy future for propulsion. So hopefully everybody got the contact info, and we'll go ahead and stop sharing at this point. And there's also the schedule that's been posted in the chat window, and there's also some other information that you might see on the futureenergy.org website, which is our conference website for all the conferences in future energy that we've currently conducted. So feel free to visit there. We'll be posting the videos on the website, futureenergy.org, after the conference to make them available. I think the transition is finally being made from DVDs to downloadable videos in MP4. MP4 seems to be the prominent format for videos, and also WMV format. So both of those will be also posted there, and also on our YouTube channel. Currently, the YouTube channel, our YouTube channel at tinyurl/IRI YouTube, doesn't currently show the live streaming. So we're still working with that. However, it is being live streamed on YouTube. It just has a different URL. So that's the only issue. Probably if you go to YouTube, if you wanted to, or let your friends know that they could tune in even if they didn't register, just search for COFE, COFE12, and most likely you'll be able to find the latest live streaming link to all of the videos and the live performances that we're offering today. So we're about to go into our break in 2 minutes, and we'll be taking a 10-minute break. You'll see a screen pop up with a timer, and then our next presentation will be from Dr. Thorsten Ludwig, who's joining us from Berlin, Germany. So this is quite exciting to bring him on board from halfway around the world. So once again, I remind you to please take advantage of the chat window. It comes directly to me. I am looking at the questions that come in and trying to respond privately if they need to. But if you have questions for the speaker, that would be the best thing for you to use in putting the questions in the chat window. And then at the end of, say, for example, Dr. Ludwig's presentation, I can then read off the questions to him and you'll have answers provided to everyone. So that would be probably the best thing to go. And so we're really excited that most of the glitches have been solved. Our sound problem, I think, was solved within about 5 minutes of the presentation. And nicely, Steve Hampton provided a very great slideshow along with his demonstration. So I think we're really on the cutting edge of energy, propulsion, and bioenergetics that you can find anywhere in the world. And we've been that focus. We've been onto that focus because that's their mission statement, to provide research integrity, researching the scientific integrity of those three areas: energy, propulsion, and bioenergetics. So we're fortunate also to have a benefactor who's helping us each month. So we're also funding Mike Gamble's research into a larger dual CMG, as it's called, control moment gyro. And sooner than later, I believe we're going to see significant propulsion that can climb an incline and perhaps even provide vehicular propulsion. So this is really the goal for inertial propulsion by any of the inventors, such as Steve and Mike. So I think we're at the point now where we can go to break, and the slides should come up momentarily. And I am happy to see how things are progressing. So thank you very much, and we'll join you in 10 minutes. Greetings, welcome back. We're at the 12th Conference on Future Energy, and we're excited to have, as I mentioned before, the physicist from Berlin, Germany, joining us momentarily for a presentation. And what's interesting is that Dr. Thorsten Ludwig currently works as a researcher at the Berlin Institute for Innovative Energy and Propulsion Technologies, and he's been researching and experimenting in this field for many years. He's also traveled to the United States for years and visited and lectured at our previous conferences on future energy as well. And his papers are on our website. He's contributed to proceedings. He's also in the latest book that I was editor for. Nova Science Publishers are coming out with the hardcover book, which is also going to be in PDF form available as well. And Dr. Ludwig provided a paper of his for that too. He conducts experiments in quantum field effect, magnetism, resonance, mind and matter interaction, cavitation, ion traps, and a number of free energy generators that he's also researched. He's also interested in the Casimir effect in his laboratory and has a scanning electron microscope that it would be nice if he ends up donating to Integrity Research. No, I'm only kidding. But it's quite interesting that also he's worked with an atomic force microscope as well. And so we're jealous of all the heavy-duty equipment that he's been able to probe the inner microscopic and nanoscopic world with. He's currently the president of the German Space Power Association, and he works with various other technical people in the field. Speaking on the topic of extracting energy from the quantum vacuum, we'll switch over to Dr. Thorsten Ludwig. Let me share the screen. Oh, good. He's also live. There he is.
Yes. Hello to everybody.
And
I'm
sharing the screen too.
Thank you very much, Tom, for the opportunity to talk about our work here. Yes, different times. Instead of meeting live, we are meeting more worldwide right here. I scanned through the list of participants and saw a number of good friends from around the world. So hello to everybody. Yes, extracting energy and from the quantum vacuum. Let's go to the introduction.
Okay.
Yes. The quantum vacuum, also many people heard about, hopefully, the 0-point energy. For many years it has been discussed. So we look a little bit at the basic concept. Then we jump to the Casimir effect, which is lucky for us. The quantum world, there's a lot of theory, but there's also very hard evidence and experiments. So the Casimir effect is all about force and energy. And then over the years, I'm also interested in the consciousness and its effects on mind and matter. And so I will show a few of our experiments, but also on the prospects that this opens up if we look at the quantum field theory. So, and also I use the time to create a new Kohler device, so I'll share that with you at the end of the talk. So the introduction to the quantum vacuum, also called the sea of energy that we live in, well, it goes back to the van der Waals force and the black body radiation, which kind of led to the quantum theory as we know it today. But then it moved on, and first there were very small systems. Then some people went to look at space in general. And of course, why are we doing this? We want new energy technologies and, as many of you, new propulsion systems. So I really like, next slide, I really like this part that nature is already doing it. You know, we still try to figure out how to use it, but this little fellow here, the gecko, He can climb walls, hang from ceilings, even as large as a couple of kilos. So, and on the right-hand side of this slide, you see he's doing that not with hooks or anything. It's just flat little hairs. The only thing that is different from to flies and spiders is that the density of and the size is smaller of the hairs and the density is much larger. So um, so if you hear about the Casimir effect, you will see why flat to flat and very close up gives most power, most force, so he can hang from the ceiling. And it's only a little bit recently, 2005, when this was discovered and unveiled. Okay, next slide. So one more thing I like to point out is that the Casimir effect and the van der Waals force, basically the same thing. It's only that the van der Waals force is between non-metals, and the Casimir effect is between metals. So the theory and how to calculate it is quite different, but the basic principle is absolutely the same. So in the late 1900, 1873, the gas equation, you see the ideal gas equation, but then van der Waals, he noticed that you have to adjust for size and also for the interaction between the atoms and even the neutral atoms in the gas, and it kind of changes the equation. So the Nobel Prize was issued in 1910. Next slide. So, so the quantum mechanics then came along, and from the blackbody radiation, and Planck in turn of the last century in Berlin gave famous speech. He was not really a friend of his own theory, but the quantization of energy, but the numbers came out nicely, and so he started this. And then the important thing on this slide is that in 1912, he added this +1/2 to his formula, which is basically the 0-point energy that we will talk about a lot more later. Yes, please, next slide. So here are a few figures, even Einstein, who some people saying, what has he to do with quantum mechanics? But he and Nernst, they were the first one to actually think larger and expand the whole idea to space itself. And then Heisenberg came along, and we know the uncertainty principle that he's famous for, but there's also uncertainty between energy and time. And this gives rise to virtual particles. Next slide. And that kind of makes up the 0-point energy. There's another way of looking at it. On the left, you see a harmonic oscillator on the left top. Classical, it can't stand still. In the quantum mechanic world, it cannot stand still. It at least has the, let's say, uncertainty of half an energy quantum. And you can also interpret that as a jitter or a random fluctuation. On the right-hand side of the slide, you can see you can expand this theory to space itself. It also has cavity modes, and these cavity modes also have this uncertainty or this 1/2 of energy as the lowest state. So in the next slide, if you sum that up over space and over the mode density and the energy per density, you come up with the so-called 0-point energy, which is a large amount of energy, which is in space itself, but most likely as a background quantum fluctuation. Next slide. Okay, well, still here Schwinger also, he expanded it more into space, and we will come back to him later and his calculation on magnetism that are important. And also Casimir in 1948, he came up with the idea that if you have, we will see that shortly in the slides, that if you have two metal plates. So if you just restrict this 0-point energy, if you make one area with more and you have one area with less 0-point energy, you can create a force. And that has been measured. Next slide. Here we see the Casimir effect. The red is the metal plates. The blue and the black lines are the background radiation, and the blue is the radiation pressure. So because between the plates there are less photons and outside there are more photons, there is a pressure to push the plates together. Next slide. So here you can see that a little bit more from the vibrational view. You can see the larger waves just don't fit in between the cavities, so they are not there. And so there's less of this background radiation. Yes, next slide. So I put this in to show that in physics, these particles, also called virtual particles, they're called virtual because in the Feynman diagrams, as we see it here, they start and end in the same picture, so that they're very difficult to detect. You can only detect particles that flow in and out of the Feynman diagram. But the virtual particles, they kind of represent the major forces, because they kind of, for example, the virtual photon transmit the electrical forces. And so forth, the weak force and the strong force also has these photons or bosons who interact and give the forces. So this whole picture is very integrated in the modern viewpoint of physics. And in the middle, you see the artist's view, where you can see points, meaning colorful dots, photons coming into being and going out of being. And so this grizzle. Next slide. So now what to do with this? One thing that I like to mention is that you can also, or at least Heisch and Puthoff made the starting point together with Sakharov, to connect the 0-point energy with gravity. And it's a simple kind of argument, and they can calculate the gravity from that. But since then, meaning here 1989, I would say not that much has happened. And I asked Puthoff directly once, can you calculate the difference between the mass of the electron and the mass of the proton from any of these theories? And they're still working on that. So next slide. Okay, for those who want to go deeper into the whole subject, especially want to calculate anything, this book is a very valuable, valuable resource showing all the mathematics behind it and how to use them. Next slide. So now we come to the what Tom mentioned, the atomic force microscope, because it's the tool to measure small forces. So in this case, it has been altered in not to look for like microscopic pictures, what the AFM is mostly used for, but to measure the Casimir force. So you see the golden or the sphere, let's say it's golden sphere. So, and you have a flat surface. You do this out of two reasons. One, you can measure pico-Newton forces with this setup. And the other reason is you use a sphere and a flat instead of two flat surfaces, like in the theoretical Casimir, because the alignment is very difficult at these, not to speak of and all the other problems that you have there, like stiction and so forth, but just the alignment is very difficult. So I know there have been groups trying to measure the so-called flat arrangement because it has much larger force, but it's very difficult, and they have not. I have not heard of anybody succeeding. Next slide. So with this setup, you can measure the Casimir force. This is how the AFM looks like. And next slide. So I think that's a vacuum AFM here. So you see in the middle under the glass, that's where the normal AFM is sitting, and the rest is the vacuum setup to actually suck out the air. That is mostly so you have less influence. You more decouple, and it's easier or better for measuring very small forces. Next slide. So now there have been a number of people, or let's say a handful of people, who publish on using zero-point energy as an energy source. And so Fabrizio Pinto and John McClay have in this community published, and next slide. And here we see Pinto on a COFE conference, of course, presenting, I don't know which one this was, but Tom will tell us later. So here he presented it. You see his drawing from his patent or his publications using the Casimir force in combination with laser technique to actually make a moving machine. Next slide. So here we see what generally the problem is with the setup if you actually want to use it. So in the upper left, you can see that 100 nanometers is what you can easily get as a distance. 30 nanometers is also possible. But below that, usually the roughness of the surface interacts, and it's not really doable. And the area of 1 micrometer is also doable at this point. So you get a small amount of energy. If you want to really use it, we have to move down to the right lower corner of this, so closer distances and larger areas. So next slide. Why is that difficult? COFE2. All right. So here we see this is a correction coefficient for the real reflectivity of the metal, which is finite, and also the temperature. So we can see that if you do it in the 1 micrometer range, they all cancel out each other. There is not much correction. So you measure the force and think, yes, I measure the right force. What Moreau did, if you go up a little bit to the 3 to 5 micrometer range, you actually get larger forces, so it's easier to measure. That's where the first modern measurements were done. But you see, if you want to go down to the left and become closer, like the 100 nanometers that I mentioned, well, there the reflectivity of the metal goes really down, and most metals become transparent. So yes, next slide. So it's with real metals, it's not so easy. So if you want to use it, we would at least need a new approach, meaning we need other structures than real metals, for example, electron clouds, or so to make them in smaller separations than 100 nanometers, or have structures that we kind of create by high frequencies, and that sort of thing might bring us closer to the goal of actually extracting larger amounts of energy. Next slide. So here we see what then happens. We go down to the pico of femtometer range and 100 square meters, then we get really large amounts of energy, like 10 to the power 17 joule, 10 to the power 21. That I think definitely would be great. But we have to be very inventive to do that. Next slide. So another totally different approach would be to use this Princeton Engineering Anomaly Research outcome, peer results. And I have only limited time to explain what they did. But in general, if you have a random process like throwing a dice or anything like that, and you ask people to use their intention, their willpower to change the mean of that. For example, tell someone, concentrate so that if you throw the dice, number 1 to 3 becomes more often than 4 to 6. So here what we see in this picture is if you actually do that with millions of people, really, then you find out that there is roughly a 0.1% chance, not chance, but that you can change the percentage by 0.1%, like that. So if you have 10,000 or 100,000 experiments, you can measure that effect. So in that sense, it's, I think, very important work, but it's not easy to redo it because you need such a large amount of people and experiments. So if we consider that this is correct, next slide, then what we can do is we could say, okay, we could use the intention, our willpower, to change the 0-point energy fluctuations. So if we would do that by just 0.1%, then it will have a much larger effect than Casimir plates out of real metal, which are kilometers large. Next slide. So here I did some calculations. The first is an important point in all the calculations on 0-point energy, the cutoff frequency. Where do we stop? So in these, I'm sure some of you have looked into the books, and there are larger numbers for the 0-point energy, but they just have higher cutoff frequencies. So I said, okay, 10 to the power 20 eV is something we have observed as particles from outer space coming into the atmosphere. So I say 10 to the power 20 eV is real, so I use that as a cutoff frequency. Next slide. So I use that as a cutoff frequency, and if you punch the numbers in, then you'll get 10 to the power 63 joules per square meter as a result. If by peer-like influence we could change the 0-point energy by 0.1%. So my conclusion is that intention has a great potential in this arena. Next slide. No, one back. That was one big guess. So what I'm also proposing is to use experiments like what William Tiller did. He was using little machines where the intention is imprinted. So intention imprinted electronic devices. And I think they are a nice way of cohering the intention. Otherwise, we think of this and think of that. And if we're not concentrated, then it will be more difficult. So he has shown some interesting ways how to do these experiments. So of course, we have to see if this is really possible. So next slide, what we have been doing in cooperation with Integrity Research Institute over the years is to work on this mental control of a single electron spin experiments. You see here the picture is, that's a technique, the ion trap. And if you do it right, you can single out ions. So for the experiment, I'm showing the 6 in a row, 5 in a row, that will be ideal. So next slide. So here is what this experiment is all about. You have a person and with some sort of a field and proposed M field, but it could be other fields. We don't know what kind of field it will be, but with some way, this little gray fellow in the middle is a spin. So in a magnetic field, the spin has two positions, possible positions: spin up, spin down. And so the transition is a spin flip. So here it's all about using the mind to make a spin flip. And what I'm showing you is that we set out and worked for, I think, about 5 years on realizing this. And next slide. So this is the mastermind behind this experiment, Professor Ron Brine, who is the mastermind, and he published this. And on some conference we got together, or some little meeting, and somehow Marco Bischoff, a friend of mine, told me, why don't you talk to him and help him to realize this experiment? And then we talked to him, and we ended up trying to realize it with him. So next slide. Next slide, please. Yes. Here's to show that this method is a very well-known method, or it's such a high-class method. It's being used widely to measure precision measurements at CERN and other places, many other places. And here you can see that in 2012, the Nobel Prize Committee thought the ion trapping is such an important experimental tool that they gave the Nobel Prize for this. Next slide. So here's our lab. And in the background, you can see two Helmholtz coils and a vacuum chamber just above the screen there, yes. And the rest is vacuum equipment and electrical power supplies and high frequency power supplies to actually power the ion trap. Basically, you have a rotating electromagnetic field that holds the ions in place. Next slide. So here in the middle, among all the rods, you see two rods in the center between the two round-up parts. So this is called the quadrupole. So there are different ion trap configurations, and the pole trap, the quadrupole ion trap, is a common one, and we thought it is suitable for our experiments. Next slide. So here for the experts, we want to use magnesium ions, and these three lines up, vertical lines, they represent the fluorescent transition. So if you have no magnetic field, then the spin doesn't make any difference, and you have only one S line and one P3-2 line. So if you turn on the magnetic field, we go to the right part, and then, yeah, you see that if you have, for example, if you have the spin up, so the upper lower one, and you go all the way to the top, then if you memorize this distance and then you flip the spin, so meaning you in the lower part, you go to the lower level, then if you don't retune your laser, then you will end up at the dashed line in the middle, in the upper part, and there is no level there. So the fluorescence, if you had before a fluorescence, meaning the laser induced the electron to go from the lower state to the upper state, and then the electron falls back and emits a photon, it won't work if you flip the spin. So next slide. So here's the laser setup that is necessary. And in all, the charming thing about this whole experiment is that we move away from the pure like random and large statistics. We move into single quantum events. Another charming thing about this experiment is that you only need point something like 0.5 micro evolt to, so like a millionth of the energy of a photo of a blue light photon in order to flip the spin. The disadvantage is that the laser needs, in order for the precision, the laser needs to have only 1 megahertz bandwidth at 297.6 nanometers, which means that for like 9 digits, your frequency, your laser has to be stable. Yeah, that's so that's the challenging, one of the challenges in this experiment. Next slide. So here the laser is in action. Next slide. Let's see what comes. Not sure. Yeah. So we do this at this facility, and if you, I think it's a great experiment. It's a very, but we haven't finished it yet. For one reason is that we need more funds to complete, especially the laser setup. The ion trap we are mostly finished, but the laser we couldn't finish it with the funds we had. Next slide. So we jump back in this talk to the area where we extract energy from the vacuum. I really think it's important to point out that theoretically, in this paper, you can clearly see the argument why it is not contradicting any physical law to extract energy from this quantum vacuum. I think that's a very important milestone. Next slide. So one more project we are doing here, again, in a little bit in cooperation with the integrity research, but mostly in cooperation with Robert DiBiase, is using the Lateral Casimir effect to as a possible energy source. I put in a few slides to show that the lateral Casimir force has been shown in this Chen Muhyiddin setup and the paper you saw on the previous slide. And what you see here, if you see again a more simplified AFM setup. So most of the stuff except the laser, the cantilever, and the base plate, everything else has been kind of removed to show it. But in the middle, you see again the sphere. You see the V on top, that is the cantilever, which is attached to the microscope. But the reflecting laser on top is measuring your force. So the cantilever is kind of reacting to the force. It tilts more or less if the force is more or less. And the laser is reflected to the photodiode. So if you have A and B as sections, the difference between A and B will give you the force. So now the lateral force here is that they don't measure the force between the ball and the base plate. They measure it to the vertical congruated plate. So that's why it's called lateral. You have the ball, you have the vertical, but you measure lateral to the plate, to the congruated plate. So we jump to the next. If you're more interested in all the details, you have to, or please read more on that in the paper. So this is the outcome. It looks sinusoidal, that's right, but you have two congruated plates, and if you kind of slowly move them, you have some areas where the points are very close. That's the, for example, the upper sinusoidal part. Then they move away a little bit to this direction. You have less force. And when you come closer to the next one, you have forces in the opposite direction. So basically what this shows us is that, yes, we can measure the lateral Casimir force. Next slide. So now, please refer to the COFE 9-11 proceedings and papers and videos and publications from Robert DiBiase. And the main thing, I think, if we go to the next slide, we'll see the most important thing about his proposal is that in the congruation, you have only one side is gold, meaning metal plated, and the other is a non-metal, is a dielectric, and also the wedge part of the surface is important, as he would point out, and he proposed that with this sort of setup, we are getting energy or also propulsion lift from this setup. Yes, so so usually Robert DiBiase will tell you all about the theory, and he did so in COFE 9-11, and it's more my part to make this with the AFM a reality. So please, next slide. So to actually measure it, here we again have our slide. So we have the sphere and the flat surface. Only now we have a congruated sphere, and that's the challenge in this whole proceeding, is to actually make this congruated sphere and also the half metal. So if we go to the next slide, yeah, we see again our AFM. Next slide. So the we tried, or we are on the way of making these spheres congruated in the right way. So we printed structures into the ball. We also used paraffin to make it even better. We considered, or we even practiced the heating, the pressing, the cutting, the scratching, and we verified the outcome with the AFM. Next slide, please. And here you see that we succeeded in imprinting the sphere, at least. What we don't have yet is the exact one-sided metallization of this setup. For example, we didn't do it here because yes, we have an imprinted sphere, but they were not deep enough to our satisfaction, the grooves. No? So we worked with paraffin, but the paraffin is difficult to coat with gold. So we're still working on, we'll probably fall back to either heat the plastic spheres to a precise temperature and then imprint them, or to use a very cold metallization process so the wax surface is not melting too much. Next slide. So this is also work in progress. This is the latest, you can see here on the bottom. In the middle, you see an AFM picture, and this is the analyzing tool. And here you can see on the white square that you can see where the red and green crosses right there. In that area, you can see that the imprinting worked quite nicely. And but in this case also, I think the resolution is not good enough to that, so you can see it. But in the blue line in the red picture just above, that's where kind of the white picture is the cut of that, the topographic cut of that line. So in that area, that lower area, we have the right lines, but in the middle of the picture, that's actually the top of the sphere. That's the lines disappear. And my interpretation is that the gold coating was too hot and it melted the paraffin in that area. So this is work in progress. And for the last years, we always have been reporting what we do in this project. And it was always very good to have the feedback and the discussion and Tom's comments on how we should proceed. So let's see how we do this. Yes, this year, maybe we get him to have a one-on-one with us so he can guide us further. So next slide. So one thing I've also been reporting over the years, and is another angle of the quantum vacuum, is the whole magnetic part. And so the Kohler generator, here is the report from the British Intelligence Subcommittee. I show this picture first because that BIOS report is readily available on the internet, and it gives you 40, 50 pages of first classified, now unclassified government class information on this whole energy generator. And so they came to the conclusion it does work. They wanted to continue, but unfortunately Kohler died out of a heart disease. Maybe he was too agitated working as a German in England just after the war, but that's all speculation. But next slide. At least we know for sure, or there's tons of evidence that Kohler really were in England and worked there and reproduced his invention. His invention is a little bit earlier. It's from the 20s and 30s. And so he next slide, please. So next slide, please. Yeah, from IRI, absolutely. Yes, I took out that part because we're not at IRI, so it doesn't, we can't really go right away and buy it, but they sell it. Having trouble advancing, well, that's too bad. So I'll work on it. We hope Tom will make it. Maybe he's in a different mode, so he can write and he cannot advance, but I hope he will figure it out. So, so the Kohler device, yes, here we go. So the Kohler device, here we see that a friend of ours, he went actually into the archive and took pictures of all the Kohler file. And so next slide. So it's quite real. And well, still having problems. No, advancing slide. Yes, please. Yeah, very good. So here we see the pictures of the so-called Magnetstrom apparatus or magnetic current apparatus. It's there's a lot more information on this Kohler device than on the other. Unfortunately, this is a device which only gives half a watt. The one that gave 6 kilowatt is of course much more interesting, but we have less information about it, because this is one he rebuilt in England. And why am I mentioning this here? One reason is that I've known many people who have rebuilt it, and all of them actually work. The thing is, you have to know that half a watt is when you really tune it well. If you tune it really well, then you get half a watt. You get less if it's not as well tuned. But let's look a little bit in what is happening here. Next slide. How is it built? You have 6 magnets, ferromagnetic magnets, not too complicated ceramic magnets. And a speciality of Kohler is that the current actually flows through at some part through the magnet. And then the whole thing is kind of a resonance circuit. So you have the tuning coils on the bottom, you have the capacitors on the top, and a switch to close or leave it open. So, and next slide, and here you can see that in the middle, the soldered and bound. So the whole coil is physically connected to the magnet, and it flows through it. So you have this is a specialty of all the Kohler devices. Very, very important. And you have right wound and left wound coils. Next slide. So we have built this 20 years ago at the University of Berlin, and I've measured this. And next slide. And here you can see a close-up of the hexagon that we just saw. Next slide. And so if you want to read about all the measurements here's the outcome. So you can see that these are snapshots of good tuned moments. Kohler describes how to tune it. It's you change the distance of the magnets, and you also change the position of the tuning coil. So, and you have to wait a little bit. And also, next slide. So here you can still download this courtesy of COFE and Integrity Research. Tom, thanks, great. You can still download it for free. And if you type in my name and Kohler, there's another one, which I'm not mentioning here. So please make a note and look at that. There you can see all the details on what we did on that first one. Now I used the Corona lockdown time to, next slide, build another one. Because I was thinking, should I measure more on the old one? Should I measure more on the 6 kilowatt, less information, more complicated device? And so I thought, okay, since years, I've been telling people the Kohler works. I think the best way of proving myself right or wrong is to build another one and see if that will work or not. And so I put in 3-4 months of work, and it behaves, it lives, it works like the other one. But it is time consuming to tune it. And at the beginning, I had to wait 1 or 2 days. At the beginning, there was nothing coming out. And then after 2-3 days, it started to come out. And then I tuned it, and it got a little bit better or a little bit less good. And you have to wait a little bit for it to settle. So next slide. Yes. Let's hurry up. So why am I saying this? I think here is a very important connection between zero-point energy and magnetism. Also, you can read that in some of my papers. But here in the picture, you can see on the right-hand side, these are the Feynman diagrams that are necessary to calculate the magnetic moment of the electron. So you can calculate the basic magnetic moment from the electron from quantum field theory. Next slide. And so maybe we hurry up a little bit through this. So next slide. It's, I think, the very important achievement of the Gyroscope or relativistic quantum mechanics, that you can calculate the magnetic moment of the electron. It comes out as 2. So not as 1, but as 2. And if you measure it more precisely than that, as Schwinger did calculating and Demelt did in measurements in the previous slide, you see that that experimental difference can be calculated very exactly from the interaction with the zero-point energy field, with these virtual photons, with these, next slide. So, so magnetism is a collective effect of these magnetic moments. The magnetic moments come as interaction from this quantum vacuum. And so I think magnetism is a very interesting point, trying to extract energy from the vacuum, and Kohler, in my viewpoint, must have found a way of interacting this in order to extract energy from the vacuum. Okay, next slide. So I think here a few more points. The ferromagnetism is so interesting because it is a collective effect. It's a dissipative structure, and it fundamentally combines the vacuum fluctuation and these self-structuring processes and cohere the vacuum fluctuation. And so it's a very ideal base for what Maury King laid out, that if we have that coherence in the quantum area, that's how he sees we will extract the energy. Yes, so I think Kohler found it out, but to really understand it, we need more research into ferromagnetism. I know there are very interesting experiments with spin waves and spin polarization, but and I see a very big connection to the Floyd suite and the Manilas device. And yeah, so we try to understand more with equipping the force microscope with magnetic sensitive cantilevers, and couldn't find Kohler's 180 kilohertz frequency right away, but next slide. I think Kohler found it. Oh yes, the last point, maybe I have a couple of minutes, because people have been asking me about the Neutrino group, energy group from Germany. So yes, here the Neutrino energy group, which proposed on the bottom next to the calculator, you see a gray sort of, it's a foil. So that gray area is a foil. And that foil basically is mostly graphene. And they found this foil gives energy. So, and there is a connection between graphene and neutrino oscillation. So they named the whole thing Neutrino. That's what I can say is they had a notary. It's been going on for a couple of years, and I've seen it being demonstrated. It's a cool foil. You can just stack it up and get more power out of it, and it does work. The question, of course, is how does it work, and is it mostly converting thermal energy, or is it converting quantum fluctuations? It's not all figured out yet, but here you can see the US patent application number, and next slide, and also at the top you can see their webpage, and here University of Arkansas also, they propose that you can use graphene and the oscillations of graphene to have clean, limitless energy. So I think it's quite interesting approach to harness energy. So I think we're coming very close to the end. So I hope I showed you that there is lots of scientific background behind the sea of energy, the quantum vacuum fluctuations, and I showed you a few examples on how people work on practically using it. And yeah, if you have any questions, I'm happy to answer them. If you want to contact me, please do so. Thank you. You may say something, Tom, now, but you have to unmute yourself. Yeah.
Forgive me for not being proficient in all these buttons to push, but hopefully I'm back on the screen and communicating. Well, we're really pleased to see such an overview of all of the activities that you've done, Thorsten. I feel that most of the questions have been aimed in different directions, but we did have one here that maybe you can answer real quickly. And that is, do you have any experience with neutrino larger models that you've seen in their labs, even if it might reach to a kilowatt level?
Again, neutrino what?
Kilowatts of power.
Yes.
He claims to have a self-running unit that produces 30 kilowatts of power. Is that apparently Holger Schubert?
I haven't heard him claim that.
Founder and president of Neutrino Energy.
No, I haven't heard him. I know him personally. I've met him recently.
Okay. So you're
he doesn't claim that. I know where they are at. They are working on having larger amounts of foil, and that's not easy. This foil is, you need very expensive equipment to make large amounts of this foil.
Sure.
Yeah. So in order to have 30 kilowatt, you need to produce a lot of foil first, because right now the foil is powering calculators, which everybody knows don't need very much power. They power LEDs, and I've seen larger stacks powering small motors. Yeah. So, but not 30 kilowatts. So in order for, I haven't heard him make that claim. I don't know that they have this. I know they have some foil, and they're working on making a lot more foil. They're investing in machines to make more foil, and then also we can hopefully we will get some sheets to experiment with it ourselves.
Yeah, sounds interesting. Well, thank you very much. We've reached our limit on the time constraints, but we look forward to having you back next year. And good luck in all your research.
Yeah.
And she's going to give us 3 minutes to prepare for the next presentation. I'm happy to start our next session. Give me 2 seconds to start our recording of it as well. I'm going to go ahead and share the screen of our next presentation. Hopefully you'll be looking at the correct present predictive connection of CO2 warming and sea level. And I'm also going to start recording this too, so we'll have another record of it that will be available on our website and on YouTube as well. Okay, my background is in physics and electrical engineering. I have a PhD in general engineering and 2 bachelor's and master's in physics. Taught community college for years in physics and electrical technology and computers and microprocessors and also environmental science. So this is the, I would say, outgrowth of my interest in the concern about the environment and the experience of using the textbook, which I have underneath my computer right now, Living in the Environment by Miller, which I used for years teaching community college. So this is a topic that's close to my heart. And especially in this day of global warming, we have a lot to look at. So hopefully you'll see some information that you can take away and act upon. The presentation you're about to see is one that was also already given to the IEEE, which is the Institute for Electrical and Electronic Engineers. That happened in November at Tufts University. And I also gave a similar presentation to another short presentation as well. But it's been published in a number of journals. The longest article, I'll give you the citation for that momentarily, but upcoming is the Journal for Atmospheric Research and also the Advances in Science, Technology, and Engineering Systems Journal, SDES, which is an extension of the previous publication of the Society for Implications, Social Implications of Technology. IEEE has their own Society for Social Implications of Technology, and that's where they entertain the environmental implications that we were talking about here. And so that was very well received there. So the important part too is that the basis is my first publication, which happened in October. The 32-pager is an open access paper. It's also available on a tiny URL /Valone Climate. So that's an easy way to get it. You could click on it right now if you're at your computer, and you can read along, because what I did for the first time in this presentation is to give you all of the main points of this 32-pager, which I never was able to do in a slideshow before, because, for example, for IEEE, I was limited to 20 minutes. And in 20 minutes, you can only show about 20 slides. And so I packed everything in really quick and finished just up to the wire. But at this point, the same 3 topics of global warming, temperature, ocean height, and atmospheric carbon concentration are covered. So the way I start this presentation is basically to give you a background. And the background is based on my own life. And that is, when I was born right around 1950, within a few months of 1950, I'm surprised at my age, which is almost 70, to look back on this 70 years and say, what the heck has happened to the world? What has happened is something that's never happened before in the history of humankind. And that is, when I was born, only 2.5 billion people were in the world, half of whom were starving. Literally about 1 million people were starving, most in India. And that was a common saying, the starving people in India, don't waste your food. As you grow up in the 50s, that was parental guidance. So this was a true, real problem that was widespread at that time. Have half the population and not enough food. So what I'm also emphasizing besides that is what Norman Borlaug did and what caused this jump in the rate of growth, which is what the dark brown line shows. The rate of growth started to really accelerate around 1950, 1960. And today we have 7.5 billion. So today the number has tripled. And the effect of the peak of the rate, which went up to 2.1%, and then started decreasing shortly after 1975, was that the growth rate, the growth of population, in other words, the quantity of population, essentially started to decline in its slope slightly, so that in 2020, we're up to this point here, and then we're supposed to level out to around 11 billion, or maybe a little bit more, around 2100. But the biggest takeaway to this graph is that it takes more than 100 years from the time that the rate of growth peaks to the time when the quantity of this population, whatever the system's population, in this case it's people, will actually start to level out. So keep that in mind as we analyze the Earth situation, especially carbon dioxide. Excuse me. So far, what I'm emphasizing is global population has tripled since 1950. CO2 emissions caused by the same people we're talking about has quadrupled. And the global energy demand, which could be a driver when you think of the CO2, has quintupled, 5 times all in the same period. So this 3, 4, 5 triad, as I call it, is a major impact upon the environment. And the main cause of it, maybe you could look at Dr. Norman Borlaug, Nobel Prize winner, as a savior of mankind back in 1960, who basically went to India, founded the hybrid wheat science. And what's interesting, this video just came out this last month, the man who tried to feed the world with good deeds and unintended consequences. It's amazing that PBS.org is where you can get this, or else on Amazon. I bought 3 of them to give away, DVDs. He's the father of the Green Revolution. And when you teach environmental science, this is exactly what you refer to as an amazing transformation of plenty, the horn of plenty, in other words, seemed to have taken place after 1960. And India hunger was reversed. They started to apply his science of hybridization to other grains and other crops, and found the best and sturdiest and the most disease-resistant ones to then breed, so that they would have a lot more yield per acre, and also be drought resistant as well. So what he told everyone at that time, and this is what I'm trying to share with you guys as well, when you look at the larger picture, which is what he did, he says, I'm giving the world about 20 years. Because he knew that the population was because of the starvation. So he said, okay, let's figure out the food problem, make sure we have plenty of food, but that doesn't necessarily solve the population problem. In fact, it exacerbated it. And so we didn't listen to his warning of 20 years. So now we're getting up to 7.5 billion, headed toward 11. We're facing the same problem again, and we still have a billion people that are starving. That is literally the estimate today in 2020. The number of starving people hasn't changed. It's just there's a lot more people that have benefited from having good food available. So in some ways, this is good news. Hopefully we regard it as an opportunity, because the more people that are available to solve a problem, hopefully we'll solve it more quickly. And the problem can be solved. That's what I'm going to show you, even though there's lots of consternation here that's coming up when you look at the facts of, for example, carbon emissions that have quadrupled since 1950. When you look at the carbon emissions, we're putting out 10 billion, 20 billion, 30 billion, almost 40 billion. We're up to about 37 billion tons of carbon dioxide every single year. Every single year we put up 37 billion tons or more. This graph looks like it's aimed upwards. We've had a little bit of leveling off due to the COVID-19. People aren't burning in fossil fuels and traveling as much, which is a great little respite for about a year. But everyone knows this is going to start shooting up again because obviously population keeps growing and we're going to overcome the COVID challenge. We won't overcome the global warming challenge, especially if we're going to keep putting carbon that stays in the atmosphere. The 40 gigatons per year, which is where we're headed to, will basically add to the other 410, actually 936 gigatons that are excessively in the air already. But what I want to call your attention to is this rate. Since 1960, this has been recorded by NOAA, and the rate is the amount of CO2 per time. Now, this growth rate has been exceeding 2.7%, not 2.1% where population peaked, but 2.7%. And do you see any chance that this is going to level out? I don't. And if the growth rate isn't leveling out or peaking, then the actual quantity of CO2 has little chance for the next 100 years of leveling out, according to business as usual. You know, we always hope for a big renewable energy influx. All the climatologists say that's all we need, just a little bit of renewable energy, 20, 30, 40, 50% renewables, and everything will level out temperature-wise. Well, I have news for you that the two aren't related, and the gigatons that are already there are the big problem. So let's look at those gigatons. So far, the gigatons are caused by this massive amount of coal, oil, and natural gas. Literally, about 90% of all the world's energy usage is fossil fuel technology. We have a huge carbon footprint that we have to solve. This is number one. And I look at it as number two because it's a long-term problem, at least 100 years before that 90% is going to go down to 10%. But so far, we acknowledge, all the world is acknowledging, especially in Europe, they're acknowledging the fact that they can make a switch to renewable energy within 10, 20, 30 years. And that's a great aspiration to have, and we should have it in the United States as well. Hopefully the next administration will take this and run with it, because all of this needs to be replaced by renewable energy if we have any hope of not having a hothouse Earth. And we're headed toward a hothouse Earth, there's no doubt about it. So let me show you the hothouse problem. And a lot of people I've talked to, I mean, there is a percentage that says, you know, I don't know about carbon dioxide, you know, the Earth is going through cycles, and they don't really acknowledge the relationship between the carbon dioxide and temperature. Well, here's the experiment from a school teacher. Take 2 soda bottles, both filled half full with water, pop in a little seltzer, Alka-Seltzer, and see the bubbles, carbon dioxide bubbles that formed here. Put the same light on both, and then read the temperature after time. The time we're looking at the bottom here is 20, 40, 60 minutes. Plain water reaches the lower steady state at around 35 degrees from ambient temperature up to about 35. The seltzer water, which is just a little bit extra CO2 added to the air above the water, takes longer to reach the steady state and levels off at 44 degrees, 9 degrees C hotter. And this is a huge amount of temperature, 9 degrees C, and about double it for Fahrenheit. So far, these numbers haven't sunk in, but maybe they will when we look at the historic record of the Earth. But this, to me, is a dramatic, as he says in his posting of the YouTube video, which you can find this entire video online, very effective, dramatic demo to show the effect of temperature and increased levels of CO2. And it's a heat-trapping gas, in other words. CO2 is the heat-trapping gas that's already in the atmosphere. And that's what I want to show you as far as the correlation. Here is one of the most referred to graphs that we don't see enough of in the daily news to to remind people that temperature and CO2 are tightly correlated. Not just loosely correlated, but tightly correlated. Every time we've gone through an ice age, CO2 goes down and temperature goes down. Every time we come out of the ice age, CO2 goes up, temperature goes up. And notice how they track each other. You see 4 ice ages here, over 400,000 years. This is the Vostok ice core. This is the most highly referred to ice core that basically then comes up to the present time. And if we view the maximum temperature and maximum CO2 that has ever been reached for 400,000 years, we're at around 290 parts per million. That is the what we climatologists refer to as the starting point or the leveling off point that pre-industrial human race worldwide got used to. We're very comfortable at 290 and the temperature around 15 degrees C, which we call 0 at this point. So that's our references. These are our reference. The horizontal lines are reference. Well, from the reference point, we're basically pushing today up to around 410 parts per million. We've gone from 290 to 410 in less than 100 years. That's a 45% increase. 45% increase of a heat-trapping gas, which has never been done on the Earth except for, as you'll see, 50 million years ago. And what do we expect for temperature at this correlated graph? Well, this graph tells us we're going to be into the 6 to 8 degrees C increase range. And it'll probably happen pretty soon. Who knows how soon? By 2100 perhaps? That's soon enough. Well, here's a geological paleoclimatology picture. And if we basically follow the trend, which I already showed you, of the actual CO2 increase, we're looking at the business as usual as A2. And the business as usual graph projects us by 2100 to be around 800 parts per million. We're at 400 now, we're headed up to 800, and 290 is our baseline. So 800 is serious, it is unprecedented in the recent history. However, if we look at the 800 we're headed to for 2100, for A2 business as usual, way up here, we can go back in time, go through our 4 ice ages, and even further, millions of years before that, and guess what? We end up at the Paleocene thermal maximum in the Eocene epoch at 800 parts per million. So it has happened before on the Earth. And the University of Washington, courtesy of, they provide us with this information. Well, here in the Washington, D.C. area at the Smithsonian Museum, Dr. Scott Wing, who I corresponded with about this, gave an entire YouTube lecture. He gave a lecture at the Smithsonian, and it's on YouTube. And he basically has this, museum historian, fossil paleontology approach to the warming that we're headed for. And so he goes back and talks about the Paleocene, Eocene thermal maximum, PETM, and it basically shows that, yep, we went up to around 12 degrees C increase over the reference point that we're talking about. 12 degrees C for 800 parts per million. We're talking about 400 parts per million currently that will drive us up to around 6 degrees. If we double the CO2, we're going to double the temperature. That's what Dr. Wing is telling us, curator of fossil plants. And he does so in such a relaxed point of view, it's almost disturbing. I even corresponded with him saying, you know, shouldn't we be talking more seriously? Shouldn't we be warning the public about how intense and dangerous this is? And he says, well, I just take the larger picture, larger perspective. And talk about larger perspective, here you go. Here's the largest perspective we can ask for. Go back 500 million years. But recently, we're, as I say, pumping up the CO2 in this little ballpark. And if we screech over here to the sea level, this is centigrade, Celsius. then we're still looking to the 0 to 6 degree. However, notice once again on this graph, the PETM, which we acknowledged was 800 parts per million approximately, is up in the same range of the 12 degree increase. So these are numbers that are beyond shocking, beyond extreme concern. These are crisis situations that are just like COVID, only worse, because it's going to impact the entire world in a long-term effect that you can talk about the overall population effect of migrants, starvation, heat exposure, equatorial region uninhabitable. It's amazing that we don't have a movie to go to about the coming heat hothouse Earth. But I'm sure it'll be soon. Hollywood will catch up. Okay, well, what effect is this having with only a few years? Here you go. Here's the researcher, James Balog, who has done an extreme ice survey of 18 glaciers. And what he found was, for example, the Columbia Glacier is losing 1 mile every 3 years. And this is the 2006 picture of that glacier, Columbia Bay, Alaska. And here's 2012, completely gone. A glacier that disappeared in 6 years. National Geographic covered it. It's basically now historical. You can go back and see the mountains. They were completely covered by the glacier only 6 years ago. And is this happening around the world? Well, yes, actually it is. Antarctica is losing about 100, actually this is 1,500 gigatons in about 10 years. 1,500 gigatons of ice mass have disappeared in Antarctica in approximately 10 years. And when we look at Greenland, surprisingly, it's double that. Greenland doubles the Antarctic ice loss. In the same 10 years, approximately, we're looking at about 3,000, a little bit over 3,000 gigatons of ice mass. Greenland will be melting so fast that we're going to see major changes, not only in the Arctic, which is only going to be a couple decades before that's ice-free. North Arctic is almost ice-free now during the summer, but Greenland is headed to be next. And I always think, well, whoever named Greenland was prophetic, because we're going to see a green land, probably within a few hundred years. And all of that, by the way, as these two melt, just to give you a forewarning, Greenland will contribute to about 10 meters of sea level rise. And you figure it takes 1,000 years or more before Antarctic will melt, that'll contribute, they say, around 70 meters. 60 approximately plus 10 is 70. So we got at least 70 accounted for between these two ice masses of sea level rise in the next 1,000 years or so. But sea level is something I'm not trying to emphasize too much. I got a couple slides on it, but I'm really trying to focus on and convey and communicate the temperature issue. Temperature in CO2, temperature in fossil fuels, temperature in GHG, which is the greenhouse gas forcing. This is a graph showing greenhouse gases and temperature. And once again, you see the graph that, in this case, is looking at the greenhouse gases forcing upwards faster than temperature can follow quickly. So there's a little bit of lag. Luckily, we do have a little bit of a lag. We're up to 1 degree, over 1 degree C change right now. And of course, the greenhouse forcing is seriously leading its way. Well, one of my heroes in life is Dr. Jim Hansen. I've met and talked with him briefly. I get his newsletter. He's written a few books, and he works at New York University, but also he was at NASA Goddard, which is actually here in Beltsville, Maryland. And what he did in 1988, which was unprecedented at the time, was to publish an article and then give senatorial testimony about the coming global warming and climate change. Of course, he was castigated seriously because nobody wanted to believe it. Well, as we look back now, and I published my article in 2019 because of this graph. In 1988, for some reason, he included 2019 as the very last data point on his NASA supercomputer projection of what temperature increase would be experienced worldwide in 2019. Of course, he's got the other years here too. But I was so surprised to see 2019 here. I thought, oh, I got to really celebrate that year. And of course, who in the world, except for Dr. Jim Hansen, would have the audacity to look 30 years in ahead and actually come up with the exact number? Exactly on target. 1.1 degrees is really what we now have seen as an increase from our zero baseline, which is 15 degrees, 15 and a half, approximately C worldwide. So we have to give him great accolades for this accuracy, tremendously accurate compared to anybody else. And he's been reviewed online many times, even previously years ago, saying, oh, he couldn't possibly be right. He won't be anywhere near what's really happening. We're never going to get up to a degree in just a couple decades. Well, we did, and we're headed up even faster. But there you go with the arrow. Once again, all these different scenarios and reviews, the middle point is where he ended up. And then he also projected into the 2060, and you can extrapolate a little bit more into the 2100. And of course, we're probably looking at the same exact projection, which we see the other experts, even Stanford University, 6 degrees, 46 degrees, which we'll see too. So all the experts are still looking and projecting, even way back from the 1988 point of view, to what CO2 is doing to the world. Well, here's my compilation of Dr. Jim Hansen's publication in 2006. In 2006, what he did is he put in a little innocent, not only the 400,000 year history of temperature and CO2, but he added the sea level information, which is a little bit more difficult to obtain, but he correlated and lined it up with the same max and minimum so that they're all in the same graph. And you end up in 2006, we were only at 377 parts per million. There's our 15 degree, I'm saying average 15 degrees global temperatures, and the NOAA projection, the same kind of information as well. So basically the information can be looked at more closely. We start from 400,000 years. And what I did basically here is to give the skeptics in the audience the chance to look at, and you can review the slideshow later if you like, which one comes first. I've heard criticism that, oh, CO2 has never in history led the temperature rise. Well, yes, it has. If you look at CO2 and just look at any particular vertical line, you'll probably find the black line ahead of the other two lines. And you see that basically anywhere you want. Go through the middle, same thing, and go through the end. Any one of these three will lead the other two. That's what you learn from this graph. It's so remarkable that people haven't, climatologists especially, paleoclimatologists, haven't studied this to the max in order to glean what I found was so easy to glean from the table that Jim Hansen published. Let me step back and explain what did he publish. Well, this table is remarkable. I've never seen a graph that gives us this kind of table. And what you see in between here are dotted lines, horizontal dotted lines. The axes are labeled with 10 parts per million difference, a linear difference, a linear scale for carbon dioxide. We don't have a linear difference for temperature, do we? Yes, we do. Half a degree for every horizontal dotted line. We don't have a linear gradation for sea level, do we? Yes, we do. 10 meters for sea level rise or decrease for every dotted line. So what I'm emphasizing, as I say, is just in this case, temperature, 20 parts per million of CO2. If nothing else you take away, then memorize 1 degree C for 20 parts per million, then just start at 290 and go up to 410, subtract them, you get 120. 290 is our baseline, where we'd love to be and stay. 410 is where we are now. Subtract the 2, you get 120. Divide by this 20 parts per million to find out what type of degree difference will be entrained by that CO2, we get 6 degrees. And that's exactly what I show here. The 6 degree difference is literally driven by the 410. That's it. That's all you can do to analyze the 400,000 years is you come back with a stark realization that all the rhetoric that we see today by literally professors all over the world, UN professors, UN experts, all the IPCC communications and reports, they all miss this point. I'm not sure why, because it's our history. It's our Earth history that we're now examining and easily taking away the relationship. As I point out here, divide by 2, I got 10 parts per million, half a degree, and 10 meters sea level rise. But to me, this is the most serious and egregious problem that we have to deal with immediately. 6 degrees is intolerable. 2 degrees is going to be serious enough. We've seen all kinds of fires and burning of the tundra. This is only going to get worse as we go to 2, 3, 4, and 6 degrees by 2100. That's only 80 years away. So you basically get the impression that the story and the picture is a lot serious than we've been told. The renewable energy conversion is good as a long-term fix, but the short-term fix has to be CO2. What can we do about the CO2 that's in the atmosphere right now? Because, take a look, here's Dr. Solomon, published in the Proceedings of the National Academy of Sciences. She takes the same perspective as Dr. Wing does. Oh, let's look at the long-term paleontology approach that essentially is projected at her point of view. There was only 7 billion tons per year being emitted in the early 2000s. Well, we're up to 37 per year now. So her projection of 4 to 5 degrees C was a little bit underestimated. That's how serious things have become in only 10 years, from 2009 to 2020. 2020. So really, this is 1 degree higher. But look at the difference of her perspective. Well, 2100 is here. You get up to the high temperature. She believes that we're going to stop emitting and somehow just sit there. Maybe that'll be true. That's exactly what this graph says. By 2100, we'll just stop all carbon emissions and stay at 410, which is unlikely. But the point I'm trying to make is that she's going to 3000. For 1,000 years, we're going to stay at 5 degrees more? I wouldn't want to do that. No way. But this is exactly what's published in the journals. And scientists aren't really communicating to the public the seriousness of what they're projecting for the long-term effect of global warming. Here's Stanford University, Brown and Caldera. Brown and Caldera have a wonderful bunch of articles on this. Their projection, once again, is in the 5 degree to 6 degree C range by 2100. So I'm trying to enforce upon the reader, the public, or the viewers, that all the climatologists agree on the actual projection by 2100, irrespective of whether renewable energy comes on board or not. If it doesn't, things will only get worse than 6 degrees. We're literally, as you know, from the previous PETM, headed much higher. But say renewable energy does come on board, we can still maintain the 6 degree as the top for 1,000 years. Well, I don't think either scenario is acceptable. And so I want to show you the most extreme revolutionary approach to solving this problem and getting back down to 290. So all this meter sea level rise, threshold of catastrophe. You can find these articles everywhere in the literature of how serious we are. Here's just a little bit of sea level stuff. As a courtesy, I wanted to show you that yes, we are looking at least a couple meters by the end of the century. A couple meters of sea level rise. It's a very slow thing. I hate to say it, but it's like the frog that's sitting in the water that's slowly becoming warmer and warmer. But the red shows us what's happening to the coastline and what will be gone by 2100. All the red stuff will be underwater by 2100, by at least on or below current sea level. So, and here's a projection of what London will look like by 2150. So let me start at the solution stage and kind of look toward the future about what can be done. First of all, we see in the literature the carbon tax has been advocated. And what's surprising is that the carbon tax is actually positive and popular if it's linked to the possibility of funding renewable energy. And that's exactly what we see in the Science Advances report from 2019. Young evangelicals also support it. We see it in the literature. This is the Washington Post 2019. And the question I need to ask is, can we even stabilize the 350 parts per million? 350 is at least a halfway point back down to something that's at least reasonable, even though 2-3 degree change is not necessarily the most comfortable, realizable limit to stay at. But anyways, the important point is the carbon tax idea that could be proposed perhaps by legislation. Well, let me at least throw another phrase at you, and that is negative emissions. Negative emissions is a really revolutionary idea. It basically comes from the carbon sequestration or carbon storage idea. Carbon capture and storage, CCS, is the concept behind this. And there is a free downloadable PDF from nap.edu 10766. And the greenhouse gases that this publication is advocating, the essential lowering of the emissions supposedly will bring us below 2 degree increase. Well, as I say, this misinformation is everywhere in the literature. There's no direct correlation between the two, but it's great to look at the long-term limits on emissions, and of course we need to do both. So this is one approach toward negative emissions. And we see even industrial utility companies looking at this possibility as well. And that's probably a very exciting, interesting approach. Well, one of the things I haven't mentioned yet, except just briefly, the 936 gigatons was the number I threw out at you. And that comes from converting parts per million to gigatons of carbon. And you end up with carbon dioxide. Well, 1 part per million of CO2 equals, worldwide, about 7.8 gigatons of CO2. That's almost 8 gigatons of CO2 just for 1 part per million. So if we're talking about 120 difference, or in this case, I'm proposing a compromise of 350, so it's only 60 parts per million. 60 times the 7.77 equals about 466 gigatons of CO2. Well, that's a lot. In fact, you'll see another graph where Chevron is talking about and bragging about their 4 megatons per year of carbon capture. Well, that's a drop in the bucket. They've got to go 1,000 times more before they're even into the gigaton range. 1,000 times 4 megatons will give you 4 gigatons. And then they still got to go 100 more to get into 400 gigatons. So this is a very challenging number that really requires a global carbon reduction program, exactly like we've experienced with COVID, only more seriously financially committed to, because the whole world is going to have to start doing this in a major gigaton capture mode in order to just stabilize our Earth's CO2 level to 350. So our temperature capture will start leveling out. And that's what we want. We want the temperature to finally level out and not keep increasing. And then, so how do we do it? Well, if we basically are adding 40 gigatons per year, that means we have to exceed the capture rate by at least, say, 50 to 100. So I'm stretching it and saying we should go for 100 gigatons for 10 years. And of course, then you get to 1,000 gigatons, which will take care of everything. But even if we go for 5 years and then 50 gigatons after that, we basically can stabilize the atmospheric levels as we work on renewable energy and implementation. And as lots of different publications state, pulling CO2 out of the air and using it can be and will be a $1 trillion business. And I want to emphasize the fact that as we saw those climate change 400,000 year graphs, it is reversible. All of those CO2, temperature, and sea level things that were going up together also went down together. So all we have to do is change one of the variables and the other two will go down as well. And the way to do it really is to reduce the CO2 in the atmosphere, bring that down. So it's no longer trapping heat. And people are doing that. This is NCSU University, North Carolina, that's developed a polymer with successive layers that can trap and absorb CO2. Journal article on that. We also published Future Energy E-News. You can subscribe to Future Energy E-News on our website, integrityresearchinstitute.org, and just scroll down the right-hand side and punch in your email. And Constant Contact needs you to do it personally in order to get our free email every month. We cover basically 5 stories that are on emerging energy, propulsion, and bioenergetics every year. And we already did cover that capturing thing. So here we get to a more serious, Jewel magazine, by the way, is very popular for these type of environmental solutions. 2018, here's a process by David Keith that essentially looks at the capturing CO2 in a large volume mode. And the costs right now are at least $100 per ton. We're basically looking at $10 per ton for a new novel approach like Project Vesta. But the ideal would be $1 a ton. But even at $1 a ton, if we're trying to do 50 gigatons a year, we're basically committing $50 billion. And this could be, if it's $10, $500 billion every year, just to grab the 50 gigatons out of the air. That's already almost 50 gigatons will be going up shortly as we surpass the 40. So we really should be aiming at twice that much. In other words, $1 trillion business, as we already saw was projected. Carbon Engineering is another company, which I'll show you another picture of, who's doing this on a big, large scale. High Tech is another company that's essentially looking at making hydrogen out of their smog and various fossil fuel emissions. Onboard electrolyzers also are being implemented and experimented with to make hydrogen. And there's novel methods for making hydrogen that are actually very worthwhile in this approach. Carbon Engineering out of Calgary, Canada is the only one I've seen with this kind of scenario. I mean, this is really impressive. for an artist even to propose the fact that, yes, we're going to start treating the atmosphere in a really big way. Gigatons are now possible when you have this kind of hardware. And of course, this needs to be publicly funded for direct air capture for CCU and CCS. Carbon capture utilization, but more importantly and more valuable is carbon capture and storage. I have to mention the trillion tree solution that I've heard bantered around. Trillion trees are nice. They take decades to grow before they even get up to the 1 ton per tree that trees normally sequester. However, when you cut them down and burn them, all of that goes back up in the air. So trees are a short-term storage medium, even if we go ahead with the trillion tree idea to temporarily over the next 100 years store 1 trillion tons of CO2, which would be great. I mean, we get that 936 gigatons out of the air, perhaps. But the important part is all those trees would have to stay living, but they don't. They basically die, fall over, and all the carbon goes back into the atmosphere. So overall, let's look at more serious approaches that capture carbon into rocks. And this to me is the most exciting and probably the most progressive gigaton CCS I've ever found. ProjectVesta.org, nonprofit, they found a green olivine rock. It's a sandy substance that can actually speed up the carbon capture, and it also deacidifies the oceans. So it's a volcanic mineral. And they found that as it weathers, it will start grabbing CO2. So their current, you'll see on their website, their current project is to experiment with this basically on a sea bed, on a seashore. And MIT Technology Review and many other journals have published Earth systems dynamics and so forth, the benefits of it. In my last few slides, simply show you other approaches. For example, as you prepare for the next several decades of heat increase, which will get hotter and hotter before it starts to get cooler as gigatons finally get sequestered. In the meantime, everyone should be using white on surfaces like flat roofs, and also on pavements, and also on your tilted roof. And for insulation, there's a much better insulation than the fiberglass stuff you buy at the hardware store. It's phase change insulation. If you look for phase change insulation anywhere on the internet, Insol Corp is one of them. There's many other companies that do sell them, and they sell them for different ranges. And they basically capture 10 to 100 times better BTUs and insulate and keep the indoor temperature at whatever you want. For example, for warehouses, you might be able to tolerate the 77, 84 Fahrenheit, but for indoor air, it'd be great to store it. And as I say, you can pick the insulation, phase change insulation that will stabilize the indoor temperature. So it's quite exciting that phase change insulation can be used on the attic insulation across. I talked to the president of that Insol Corp, by the way, and he essentially said that he was able to, for a warehouse, literally prevent them from installing air conditioning. And instead, he had just installed phase change insulation across the top. That's how powerful this stuff is. And the last thing I should say, temperature indoors only goes up and down 2 degrees when you do this correctly, even though the outdoor temperature could be 89 degrees. And in regards to worldwide renewable energy, this is probably one of the more exciting proposals. 100% renewable in 139 countries. He has YouTube videos explaining it. Mark Jacobson is the name that you need to Google to see this wonderful video. He has several videos. By 2050, he says 139 countries that he names can all switch to renewable, and he shows how it'll create jobs and also, of course, get rid of the fossil fuel problem and emissions problem, which is my main concern. So there's my article. You can download it for free, tinyurl/Valone Climate. And hopefully if you pass out this article, pass the website link to other people, try to let your congressman know that this is a serious issue that needs to be addressed. And the way to address it is by carbon capture. This information and the solution, gigaton carbon capture, has not been popularized or promoted or advertised at all, but we certainly need it in order to finally solve the problem once and for all. So I think we're at the 10-minute break time, and so if you do have any other questions, feel free to email me But at this point, it looks like I'll probably move on to going for our break. And however, I guess we do have our lunch break coming up, so maybe we can forego the 10-minute line. And let me see what I can see here. Princeton University says that CO2 is irrelevant. Yeah, that's a problem. Experts look at methane, for example. There's another question about methane. Well, we can look at methane all you want. And if you do the numbers, you'll find that methane has about literally 5% effect on temperature. Even if you're looking at the whole tundra releasing tons of methane that it will do and is doing now, it's still a small drop in the bucket compared to the atmospheric 40 gigatons going up every year. CO2 is a heat-trapping gas, and is the major impact is from the CO2 that we're emitting. So this is basically the issue that is happening. Of course, there are nice agricultural solutions. I see some questions about our agricultural effects. The video, The Man Who Tried to Feed the World, is available on the pbs.org website. I highly recommend it for people to consider looking at the history of our last century, and basically the ancient grains and fuel that's required for creating biofuel. Biofuel is definitely a controversial subject. Biofuels seem to be great, especially when they're developed by renewable energy. Essentially, if we're capturing CO2 to create the biofuel and then releasing it, it's carbon neutral. So essentially, it's great to see the transition, but our institute hopes for and is aiming for the electrical type of energy, propulsion, and even electric clothes and electrification for electrotherapy. It's amazing how all three program areas find benefits from electricity. And of course, I should end with the surprising insight into electrons. And of course, we'll have other people talking about electrons, such as Bill Alec tomorrow, the secrets of electrons and electron spin. But I thought I'd leave you with a little bit of a joke. Years ago, they claimed that Edison came up with an idea about selling electrons to the public. And he developed utilities, and they charge money for buying so many electrons every month from an electric utility. However, the agreement that you have to sign with the utility is that if after you buy the so many electrons, you have to give them back to the utility so they can resell them back to you next month. Which is actually a very true scientific fact, but it's surprising that the electron not only has an infinite, almost eternal lifespan, it doesn't decay, but also it has to be recycled as well, just like the proton, interestingly enough. So I thank you for your attention, and let's take an hour break time for lunch, and then we'll come back at 2 p.m. Eastern time for the presentation, live presentation by Mike Gamble. So thanks again. Well, welcome back, everybody. We are at the 12th Conference on Future Energy, broadcasting all over the world. And we're happy to have our next presenter, who essentially has the interesting background of bachelor's degree in electronic engineering from Northrop Institute of Technology. And he graduated magna cum laude from there, worked 10 years for various other companies, and then started at Boeing Aerospace back in 1985 and just retired a couple of years ago. And over the past 29 years, he worked on many different programs for Boeing commercial and classified aerospace ones. And that's where I became interested, because he presented at one of our space conferences, space and technology conferences called SPECIF. And I was fortunate and lucky enough to see a couple of photographs that he carried with him of the room size inertial propulsion devices that he worked on. And of course, the first thing that I came as a half engineer, half physicist, concerned about the public, saying, oh, is it possible we can declassify this and bring it to the civilian use? Tabletop model. And of course, that was over 6 years ago. And sure enough, we are successful to announce today, you are the first crowd to actually see the results of Mike's very diligent work and analysis of the device that he worked on to produce such a tremendous unidirectional force from electricity. This is electric propulsion. And he has experience with nitinol, actuators, and various other control moment gyros. So that's what the CMG stands for, Control Moment Gyroscope. And the room size model has now been reduced to a tabletop model. We are working on a journal article to report this. And I'm happy to say that it gives me great pleasure to introduce Mike Campbell. And instead of playing a recording, I believe we're going to have him present live so that you can actually see and hear from his excitement for this particular successful presentation. So let me share the screen of the slideshow. And if Mike is still on board, yes, he is. He's being spotlighted. We have Jackie in the background co-hosting. So I'll stop talking and let you take over, Mike.
Well, okay, I guess I'm ready to go. For those of you that haven't met me, I'm a retired electrical engineer out of Boeing, where I ran a laboratory building all kinds of fun stuff for the past 30 years. Tom Valone, conference chair there. I don't think he needs any introduction. Next chart there. This is the part 4 presentation of the continuing work on differential CMG gyros. Parts 1 and 2 and 3 are history. And so we're going to concentrate on improving the gyro system's efficiency with the goal of self-propulsion. Next chart. For those of you that haven't seen the previous presentations, we'll start with a quick review to get everybody on the same page. Next chart. This is the part 1 picture showing the left and right side views of the first test article with the gyros mounted horizontally. It's built from solid aluminum plates, weighs 17 pounds. Next chart. The part 1 conclusions, the demo unit and its documentation shows that the differential or scissoring gyros will produce a linear force. Moving on to part 2, oops. Yeah, there we go. Part 2 is the pictures of the left and right side view of the modified test article with the gyros mounted vertically and all the Swiss cheese lightning holes. It's down to 12 pounds. Next chart. Conclusions from part 2, changing the test article's K factor, which is the radius of gyration, by reducing its weight. And then we had to recalculate it. It come out to be about 16.1 inches on the y-axis. And then also calculated and measured the best neutral base angle for the maximum force generation to be between 15 and 20 degrees. However, all the optimization work did not achieve the force needed for self-propulsion. This is the last part 3 picture showing the left and right side views of the ABS plastic test article. And the gyros are mounted vertically and it weighs 7.5 pounds. Next chart. Conclusions from part 3, lightening the test article from 12 pounds down to 7.5 reduced its rolling resistance with only a slight increase in the vibration. The aluminum one required 3 ounces of average force, and the ABS plastic one only 2 ounces. However, the radius of gyration did not change that much. It went from 16.098 inches for the aluminum to 16.509 for the ABS plastic. Therefore, the force didn't change that much, from 1.024 ounces for the aluminum to 1.097 ounces for the plastic version. The one that had the greatest effect was changing the reset pulse from time average to a slower speed, increasing the peak generated force by reducing the negative portion of the pulse. The gyros only generated 1.097 ounces in the y-axis, which is estimated to be a little bit more, about 1.127 ounces in the x-axis. However, it takes 2 ounces of x-axis force to make it move. Okay, this starts the real part 4 here, the real engineering of increasing the gyro system's efficiency. Next chart. This tabular short list of the test article's weight started by drilling the holes in the original part 1 to get its weight down from 17 to 12, and then made it out of plastic, got it down to 7.5 pounds for part 3. This part 4 now is still the plastic test frame with the gyros offset, x-axis orientation, and it now weighs 9 pounds. The additional frame structure, screws, and offset plates added about 1.5 pounds. Okay, you're already there. The 6 design goals for part 4 here is we had to change the gyro orientation back from the y-axis to the x-axis. That also involved replacing the load cell with an accelerometer, and then to offset the gyro's servo axis rotation about 2 inches, and then recalculate the radius of gyration, and then to optimize the servo rotation angle for maximum force output. And if it generated 2 ounces or more of average force in the x-axis, it would be self-propelled. Okay, design goal number 1 there is to change the gyro orientation from y-axis to x-axis, which required adding 2 additional frame rails and screws, which added some more weight. This is a picture of it, right, left and right side views with the offset gyros weighing 9 pounds. Okay, next chart there, design goal number 2 is to change the test article from the x-axis to the y-axis. Well, that involved replacing the load cell, which was a force sensor, with an acceleration sensor, as it didn't work in that orientation. And the reason being, it's a compression load cell that you see there. The force arrow is showing in the down direction. It only measures it in that direction. It won't measure in the up direction or anything else. Next chart there. The way I used it for measuring the y-axis forces, I preloaded it with some of the weight. I put it under the front lip of the test article, and then that was preloaded with about 40% of the weight. And then it gave very good readings. However, when I switched over to the x-axis, I tried mounting it on the front and then pulling it up against a wall or a fixed barrier with pulleys and weights, and then that didn't work. So I tried adding bungee cords on top of that, and still didn't work. So I had to change it from a load cell to an accelerometer. Now I noticed in Steve's pitch this morning, they put it up against a solid wall, and they had better luck than I did. So I decided to change it over to an accelerometer, and that worked okay. Next chart. This chart shows the running gyro servo combination in the y-axis. There's 6 volts on the fast power stroke and 2.8 volts on the slow reset stroke. The directional pulse, that's the dark blue square wave there. It's a 1 for a power stroke and 0 for reset stroke. In theory, the output force, which is purple there, this scraggly line, should be about the same in the x-axis. Now, what happens with the slow reset, you get the power pulse and then it tapers off. So it's, oh, you're doing it? I was just going to do it, but okay. And therefore, it is now a polarized wave shape rather than equal amounts above and below the 0 point. Next chart there. This is a close-up of the accelerometer circuit, the internal picture there. It's got a little chip there, that's the accelerometer. And then its mounting location on the front of the test article. Next chart. This chart shows the schematics of the IC chip accelerometer and then associated electronics around there. Basically, it's a filter to take out the noise, which is selectable. The main one there is the scaling factor, which is 1G is equal to 300 millivolts. And then this system is scaled so it plugs into the load cell amplifier, which has a DC gain of 1.317 and an AC gain of unity. Okay, next chart. This is MATLAB simulation. The blue line there is the power and reset stroke. And then the purple here is the wave shape minus all the vibration that you've seen in the real picture. Now, what I was expecting when this thing cycles from 20 degrees and back, I was expecting a positive acceleration pulse, and then it goes to 0 on acceleration when it's moving, and then a negative acceleration pulse to stop it. However, what I got was an acceleration pulse this way, a deceleration, and then an acceleration pulse again, and then these tapered off. As the reset. And so what it appears to be showing on acceleration is the acceleration and deceleration of the servo rather than the frame, which is a little strange. I was expecting the frame to integrate the acceleration pulses and then come up with an overall frame pulse. However, that's not exactly what it shows. Okay, next chart there, please. Okay, we're going to move on to design goal 3, which is the modification to the servo axis of rotation. This picture here shows the frame side view, the two gyros. They're offset a couple inches there. We can zoom in on the next chart there. And the normal axis rotation used to be right here on top of the gyros. And so we got another gyro ring and some offset plates to make 2 inches, so that the axis of rotation is moved from the gyros 2 inches back. And what that does, it provides a small moment arm, which would help generate a little bit more force. The penalty is it costs you a little bit of speed because the servo has to sling a heavier mass. Next chart, please. The way this works, by adding this offset arm, the gyros used to be separated at a fixed 4 inches. Well, this now adds a variable 2 inches to both sides. So the separation distance changes from 6.8 inches when it's at 45 degrees to 8 inches when it's at 0 degrees. So the separation distance becomes a variable as the angle of rotation. And on the power stroke, the phasing is that it is increasing, and then as it resets, it's decreasing. So that also works in the right direction. Okay, next chart, please. Then, of course, we have to recalculate the x-axis rotational inertia, and there's 2 ways to do it. You can use textbook equations on mass and radius, or you can use the lookup table cheat sheets based on area. We'll start with the first method there, which inertia is equal to mass times radius squared. Well, the device weighs 9 pounds, so you draw a free body diagram, 9 pounds. The center of gravity of the device is 1.07 inches from the center, and then you add the d distance, which is the rotational offset that you want to find or calculate. So when you convert all this to metric, you got the 9 pounds divided by the 2.2 to get to kilograms. And then you take the d separation distance plus the 107 inches, square that, divide by the 37.7 to get to metric. You wind up with 4.082 times d plus 107, and square it and divide by the 39.37 squared, you get kilogram meter squared. Okay, the next method is using lookup tables based on rectangular plates. The numbers you need is the width and the height of the plate. You square those and then divide by 12. That gives you the rotational inertia about its center. And then we want to do it on an offset distance d, so you have to add a d squared, and then that comes up in kilogram meter squared. So then you got to go through a long, tedious process of doing all the plates. So starting with the bottom plate, it weighs 1.021 kilograms. It's 10 inches by 13 inches. You square those, divide by 12, add your offset distance, convert to metric. Then you go to the front plate, which weighs 3.05 kilograms. It's 8 inches by 3/8 of an inch. You square those, divide by 12, and then this one is offset 4.375 inches in the x-axis, so it's a D minus. Square that and then convert to metric. Same thing goes for the rear plate. It has same dimensions, only it weighs about twice as much. It's 0.680 kilograms because it carries the electronic package. You do essentially the same thing. The only difference is this one is offset a plus 3.75, and then you convert to metric. Going down to the gyros themselves, the two gyros weigh 1.863 kilograms, and they're on the center line, so it's just D squared converted to metric. And then the side plates, the two side plates weigh 1.28 kilograms. They're 9 inches by 3/4 of an inch. You square that, divide by 12, add your offset, convert to metric. And then the top plate weighs 0.085 kilograms. It's 8 inches by 2 inches. Square those, divide by 12, add your offset, and convert to metric. Then you have to go through and multiply all these out, the squared terms. You sort it all out, add up like terms, and what you get for the final total is 4.082 kilograms D squared plus 0.804D plus 11.847 divided by 39.37 squared kilogram meter squared. Then you set the two equations equal and solve for D. Now by inspection, you can throw out the 4.082 kilograms and the 39.37 squares, and you just set equal what's in the brackets. When you do that, you can throw out the D squares, and you come out with 2.140 minus 0.804D, 11.847 minus 1.145. You work that down, D is equal to 8.011 inches, and in this case, K equals D. So the x-axis radius of rotation is 8.011. Okay, next chart there. Now you take those numbers and you put them into the gyro force equation, and everything else stays the same. The gyro rotation, the servo rotation, the dimensions and that. Now this gyro separation distance was increased from 4 inches to 8 inches. That's in red. And then in blue, the gyro radius of gyration used to be 16, it's now 8. So the separation distance was doubled and the radius of gyration was half. So when you crunch all those numbers, you now come up with 0.52 pounds of peak force. It used to be down around 0.2 and 0.3. So the output force is increased. Now, in working with the offset gyros, I discovered a much simpler method of calculating the output force using the standard F equals ma equation. How that works is you do the center of mass of the gyro assembly. So you start with the motor, which weighs 2 ounces, and it's a ½ inch in the negative direction. Right now, the heavy line here is the axis of rotation, so it's a -5. And the gyro ring weighs 0.47 ounces, but it's 0 because it's on the axis. The two spacer plates weigh 0.89 ounces, and they're at 1.25 inches. The gyros themselves weigh 5.11 ounces, and they're 2 inches off the axis. And the counterweights weigh 4 ounces, and they're 3.5 inches. So you multiply and add that up, and that equals the total mass, which is 12.47 times the center of mass, which you calculate, comes out to be 1.95 inches. So the center of gravity of the unit is just shy of where the gyros are. So you have two numbers here, 12.47 ounces at 1.95 inches. Next chart. So then you plug this directly into the F equals MA. Now I took all the metric conversions and the doubling for two gyros and everything, lumped it together up front. So you put the 12.4 ounces in for the mass. Now the distance it actually moves is a little different. The mass moves on an arc because it's a fixed radius of 1.95 inches. However, the slight excursion outside of the x-axis is canceled because there's another gyro that's a mirror image of that. So the mass actually transfers a straight line in the x-axis, and by triangulation, it's the hypotenuse over the opposite side times the theta or sine theta of the angle, so it's RA sine theta. Now it takes 75 milliseconds to travel that distance. So when you plug in the numbers, now this is with the gyros not running, it generates 0.48 pounds of peak force. Okay, now design goal 5 is to optimize the gyro's servo angle of rotation for maximum force output. And I use the oscilloscope and that for the data. Okay. So I start by setting the servo to run from 45 degrees to 0 and then back. And then this is with the gyros not running. So you have a peak power of 140 milliseconds on the power stroke. Now you can see still has this funny acceleration. You get your power pulse here, and then it tapers off on the reset. Reset is 650 milliseconds, and it generates 100 millig's of acceleration. And then we change it. Then we change it from 30 degrees to 0 and back. And that shortens the power pulse and also shortens the reset and generates more force. So you now have a 95 millisecond power pulse, a 500 millisecond reset, and it generates 117 millig's. Okay, next one, we go down to 25. Same thing, the power pulse gets shorter down to 80 milliseconds. The reset pulse gets shorter down to 380 milliseconds, and it generates 200 millig's of acceleration. And then we go to 20 and do the same thing. We're down to 75 milliseconds on the power stroke, 300 milliseconds on the reset stroke, and it generates 300 millig's of acceleration. And we go down shorter, down to 15. The power stroke goes to 70. The reset stroke goes to 260, and it generates 183 millig's of acceleration. Now we go back to 20, and we turn the gyros on, and you can see a lot of background noise. So the power stroke is still 75 milliseconds for 20 and 300 for the reset. But now the accelerometer is 483 millig's with the gyros running. You can still see the pulse that tapers off here. However, the system now is operating with much more mass. Next chart. Okay, so we line them all up here, starting at 45 down to 15, and you can see that 20 is where it maxes out at. So you got 307 millig's with the gyros not running, and when you start them up, it goes to 483. The corresponding voltage is 183 millivolts versus 290 between running and stopped. So that increased quite a bit. Okay, now we do the number crunching with the gyros running, going back. Everything stays the same except for the gyros. Now, taking the ratio of the voltage differences, turning it around, and then adding the initial offset multiplied by their weight, which is 5.11 ounces, you now get 6.79 ounces, which is an increase in mass or single dimensional mass, inertia, whatever you want to call it, of 36.4%. So the total mass now goes up to 14.33 ounces. And when you calculate the center of gravity there, it's 1.96 inches. So the offset did not change very much from 195 to 196. However, you gained 1.86 ounces of mass, which is essentially a freebie. Okay, now then you dump that into the F equals MA equation, the 14.33 ounces and the 196. You run the numbers and you come up with 0.55 pounds, which is very close to the 0.52 pounds from the original equation. However, this method is much simpler and much faster to calculate. Next chart, please. Okay, then you take the peak force pulse and you convert that to average force. And basically what the equation is, it's half the peak force divided by the square root of the duty cycle. So you take the 0.55 pounds, and then you have a duty power pulse of 75, and the period is 375 milliseconds. It's 300 milliseconds for reset plus the 75 for the total of 375. You work that down, you get 0.123 pounds average force. You convert that to ounces, it's 1.97 ounces. According to the oh, well, okay.
The 2 ounces really work.
Yeah, as the gyro shows, it just barely moves because the force calculator is 1.97. However, it's pulsed at 0.55, so it will break the static friction and move. However, I'm having to hold the cables up because the friction drag, if I just let the cables drag on the bench there, would be enough to stop it. It's just marginal.
Congratulations, Mike. Yay. I can watch this enough times. Instant replay. The crowd goes wild. We waited 6 years for this. All right. And the next model will be twice as big, right? Might as well give them a preview, a little bit of a analyzing preview.
Yeah. You want to throw up the next chart here when it finishes there?
No, I don't. I want to go rerun one more time. Okay.
Anyway, the conclusions there. Oh, okay. Changing the gyro orientation back to the x-axis, forced changing the load cell to an accelerometer. And then we modified the gyros with a 2-inch servo axis offset. Next chart there. Okay, and then recalculated the x-axis radius of rotation, optimized the servo angle for maximum force output. And the calculated number is 1.97 of the required 2 ounces. So it's close enough that it should move. And being it's pulsed, it should break the stiction. And however, the frictional drag, when you run it, if the cables were dragging, it's that close to not moving. If you look at the camera angle, it looks a little funny, like I'm dragging the cables ahead of it. However, my son was behind me with the camera and I'm holding the wires perpendicular to the carriage and then moving with them. However, it does look like I'm leading it if you look at the video there. Next chart. I have some proposed modifications. One I didn't get time to do was to try different servo axis distances. I just worked with 2, but I need to go back with 1 inch, 1.5 inches, and 2.5 inches and see if I can optimize that a little bit. It was getting too close. I usually work about a month up before the conference, and then I stop working and then do all the documentation, get the presentation together, and then I start going again after the conference. And as Tom mentioned earlier, we're working on getting bigger gyros built, and we're probably going to need to put some bigger torquer motors to go along with them. Next chart. If anybody's got interest in gyroscopes, this is the website we use. It's a very good one, gyroscopes.org for information and parts and service, gyroscope.com. And next chart there. Hopefully I haven't bored you all with all the numbers that engineers love, and I thank you for watching the presentation on part 4. If anybody's got questions or comments, I'll try and answer them.
So far, we haven't had too many questions come in. Okay, well, the one question that did come in, Mike, is what is the object that would be propelled? A whole satellite? The force seems to be in the range of existing ion propulsion. So there's a knockdown, drag out.
Well, okay, the units that we have in orbit generate a couple 100 pounds of force. And they're used for station keeping, mainly for geosync satellites. Also, the ISS, the space station, has 4 big gyros on it for the same purpose.
So I guess the next logical question would be, will this model, as it goes up in scale, like double the size, be useful and maybe competitive for private competition to Boeing? Or to, who knows, some space shuttle, space...
Well, Boeing already, this is not a unique system to Boeing. All your aerospace companies that put satellites up have this essentially the same design on them.
Wow.
That's how you keep them in orbit up there. You go out to, was it 22,600 or something like that, 22,600 to geosync. And then because orbits are non-stationary, they move around a little bit. So you have to do what's called station keeping to keep the antennas plugged or pointed in the right direction.
Sure.
So you have to fire these things up every now and then to keep them pointed.
Good point.
And that's how they can keep those satellites out there for years, because if they were using propellant, the gas tank could get empty and the satellite would be junk.
Right. And that's what electropropulsion in the patent literature is referring to, just a bunch of compressed gas with an electrical actuator. So this is great that your device may actually become smaller and more efficient. Who knows? But it's certainly very promising so far. Okay, we have another question. If the whole unit was able to turn on its forward travel axis, wouldn't forced precession be a great benefit?
Well, forced precession is what it works on.
That's what I would agree with you, yeah.
Yeah, and then because of the differential operation, the off axis is canceled, similar to the Dean gyro from Steve's presentation. When you have 2 systems working alternately, the forces add in one axis and are canceled in the other axis.
So forced precession is the principle by which you're...
Yeah, the Dean drive used rotating masses. This uses forced precession of gyros. It accomplishes the same thing, which is a force in one, well, it's actually in single axis, two dimensions back and forth, a vibration or oscillation, and then you rectify one direction. And there are many methods to do that.
Mm-hmm. This seems to be a smoother method for operating, especially if you get to higher speeds and so forth, than having eccentric weights, perhaps.
Well, it all depends on how you rectify it. That's what I consider the secret. Steve uses a solenoid and then a sliding carriage for his rectification. There is another method for rectifying rotary weights, is to add the second harmonic. You have another set of counterweights there running at twice the speed. Will also rectify rather than using a solenoid. And then the method that I'm using here is you use the gyroscopes, you force process them. And then you change the speed of the precession on the power stroke versus the reset stroke. And that does the rectification.
And I guess, are we actually rotating at several thousand RPM on the gyros?
16,000.
Right now?
Yeah.
Oh my goodness.
That's that whining sound you hear like a bumblebee.
Wow.
I'm amazed the bearings haven't blown out on me yet.
You don't have like a bulletproof shield between you and the device. I remember years ago, I used to know Robert Cook, and he wrote the book Death of Rocketry. For the sake of the listeners who may be younger than we are. And Death of Rocketry was very, science fiction oriented, with lots of pictures of electrically powered rockets, flying vehicles. Do you think inertial propulsion of this sort will ever be advanced and developed sufficiently to, say, levitate a mass of maybe one person?
Well, you'll never blast off with it, but once you get into space where you lose the weight, you still keep the horsepower, so it works great in space. But as far as blast off, like the big one we had at Boeing there, it generated about 400 pounds of thrust. The problem was it weighed 1,500 pounds.
Sure.
So it doesn't have enough horsepower to lift off, but once you go into space and you lose the 1,500 pounds, you now have a source of a couple hundred pounds of thrust.
Wow. And that's basically what this would do as well. And maybe it won't even weigh as much, but who knows? In other words, for space travel, it still might get us from the moon to Mars or from the space station to Mars.
Well, yes, I still think electric is the better way to go. My experience being an electrical engineer is anything you can do mechanically, you can usually do electrically, and it's simpler. Because when you do something mechanically, you got to deal with bearings, motors, and friction and vibration. And a lot of that doesn't exist in the electrical world.
That's a good point. We have a contrasting criticism from New Frontier Technologies. The satellite gyros don't use this principle, according to his opinion. They use standard high-speed gyros and motors that rotate the satellites, but no linear propulsion is derived. And I think it's maybe the public opinion that he's voicing, because I thought so for years as well, until your proprietary revelation and you got permission to reveal for the first time to the public what Boeing was doing behind the scenes.
It all depends on how you turn the gyros. Right now, they're both turning the same direction. If you turn one the opposite direction from the other, it will generate torque. And if you rotate them together in the same direction, still scissoring them, you can generate linear.
See, so it's a real simple, I mean, a textbook perhaps could be written someday now that it's public domain to educate mechanical engineers about this new development. And then inertial propulsion won't be such a hidden science. Of course, the physicists need to catch up too. That's my question, why the physicists keep telling you this is impossible and it violates the conservation of momentum.
Well, Boeing's been doing it since 1960. That's when they developed it. I presented a historical review, which Boeing authorized.
Yep, and that was a great review of what Boeing did. But you still violated physical laws, so it's being suppressed actively by every science professor in the world.
Well, all you got to do is go out to geosync orbit, and every satellite out there works on that principle, to the best of my knowledge.
I mean, this is amazing. And then that's really where we come in, because I love discovering this stuff that violates laws that are antiquated from last century.
Well, my opinion is it doesn't violate any laws. The theory has to catch up with reality.
Good point. Good point. And the newest league question or comment is from Maury King, who says, Boeing should be punished and fined for violating the law. Okay, we got another question for you, though, a real question. Can the force be enhanced by speed up the rotation of the gyro?
Yes, there's three items that control the force. One is the rotor mass, the rotor speed, and the servo speed. And then the other one is the frame's inertia and calculation, separation distance, and rotational inertia. But the two primary ones are the servo speed, gyro speed, and mass.
And which will you be doing for the next model?
Hopefully both.
If we can fund everything and make it happen.
Well, we'll give it a shot.
Okay, sounds good to me. And I suppose in general, do you see like a company or an industry being formed in the next few decades for this type of propulsion system, where you sell little boxes of force generators that you can put on your car? For example, I always wonder if this was developed sufficiently, whether you could put it in your trunk or wherever on the vehicle on land, and then basically slow down when you're traveling on slippery ice, for example, in the winter.
Well, there's already been some gyro, I think it was a truck or a bus there where they had a big gyro on there, and they used it to for both regenerative power also, where when it went downhill, it would spin up the gyros.
And well, that's for, what is it called? Braking?
Yeah, dynamic braking, but it also supplied power.
It supplies power.
Yeah.
It reserves the power.
The gyro was connected to a generator, and then they had traction motors in the wheels. And then the gyro would spin down, supplying energy to the generator, which turned the wheels. And then when the thing went downhill, it would spin the gyros back up.
Yeah. So that's dynamic energy conservation, I guess.
Yeah. The only problem they ran into, which a lot of people have hit, the other one is unless you have the gyro mounted on a 3-axis gimbal, if you try and turn the vehicle, it'll turn one way much better than the other way because you're processing the gyro, which could be a problem. Now, they ran into that back in World War I, the Lerone rotary engine. The French built an airplane engine for the old biplanes where they had the crankshaft stand still and the cylinders turned, and then the propeller was bolted right to the cylinders. Everything worked great as long as you're flying flat and level, but when you put it in a dive, it would only go left. You couldn't dive right because of the precession of the gyro.
Oh no. Wow. A little bit of a problem there. We have a couple more, one more question that is Paul Laviolette's asking about the Sequest device. He says that thruster number 1 is actually working in some other tests that we haven't heard of, but if it's possible, he'll send you information that Boeing might take advantage of, if the thrust is sufficient, I suppose.
Well, it all depends on what you're trying to do. I mean, for like I said, it won't blast off, but if you want it for just, you know, small maneuvering.
A few hundred pounds of thrust is really what you need to influence Boeing's technical implementation, probably. Yeah. Okay. Well, we're reaching the 10 break time for 10 minutes, and it sounds like we have a great industrial opportunity here, and luckily we do have funding for your next phase. of upgrading the satellite maneuvering mechanism, and hopefully it'll be finding other applications as well. So
Well, we'll keep plugging along.
sounds great. Thank you very much, Mike.
Okay.
So we're now at the point where we're going to break for another 10 minutes, and Jackie is putting up the slide. And so thank you for being part of this great opportunity and adventure. See you in 10 with Dr. Dean Radin. Welcome, everybody. Welcome back. We are excited to have our next speaker participate in our conference for the first time. And I'm pleased to be able to start recording our entire presentation. So this will be available online. And I'm just bending over to move around the camera that's right in front of the screen here for your benefit, of course. Our next speaker is Dr. Dean Radin, who's the chief scientist at the Institute of Noetic Sciences and distinguished professor at California Institute of Integral Studies. He earned an MS in electrical engineering and a PhD in psychology, which is from the University of Illinois, Urbana-Champaign. And before joining the research staff at IONS, which is the Institute for Noetic Sciences, Institute of Noetic Sciences, that Dr. Ed Mitchell formed years ago. I used to know Ed Mitchell personally, and so I had his psychic exploration book on my shelf for years, and always was amazed how this institute developed so well and strongly to bring this science into the mainstream of scholastic study. So describing what Dr. Radin has done throughout his career, he also held appointments at the AT&T Bell Labs, Princeton University, University of Edinburgh, and SRA International. He's given over 500 talks, interviews worldwide. He's 4 book chapters, technical books, and lots of different foreign language, 15 foreign languages translations from the 4 books he has in print right now: Conscious Universe, Entangled Minds, Supernormal, and Real Magic. And I might as well show these. I've had these on my shelf for years. I'm not sure if it's coming through. There you go. I have a virtual background, so sometimes it'll filter things out. Supernormal is also an amazing book because it really shows the human potential that's available throughout the world, if people even know that such performance capabilities are available. So without further ado, I will go ahead and share screen to show you his recorded presentation, and he will be and is available for question and answers afterwards. So please take advantage of the chat window to type in your questions now and during the recording so that I can read them off to Dr. Radin as soon as we're finished. It's about a 30-minute video presentation, which is actually extraordinary. I think you'll enjoy it quite a bit. Okay. I'm getting feedback here that tells me I should reload it. Sorry for the delay. Okay, we'll try sharing the screen again.
Slides.
I'm talking about
the scientific resurrection of magic. Because I'm talking about magic, I want to first do a little background check here, because you will not see any magic in my educational background and my work experience, at least not on the surface. So my first real job after getting my doctorate was at AT&T Bell Labs. I also worked at SRI International, at Princeton University, and the University of Edinburgh. I've given invited talks at Harvard, at Stanford, Columbia, the University of Cambridge, and about a dozen other universities around the world, to Google, to Johnson & Johnson, to Merck, to the government and business leaders in Australia and Malaysia. I've done programs and documentaries for almost all of at least the English language television networks around the world, and in some other languages as well. And to Naval Postgraduate School, the Naval War College, DARPA, and the U.S. Army Special Operations Command. For the past 20 years or so, I've been a scientist at the Institute of Noetic Sciences in Northern California, and also I'm a professor at the California Institute of Integral Studies. So all of that could be completely conventional science, and much of it is, but I've also always been interested in magic. And you'll see the relationship between magic and the topics that I specifically study in a minute. So what is the bridge between science and magic? The bridge that science can study? Well, it's human experiences that transcend time and space. So what are those? Those are mystical experiences, psychic experiences, and magical experiences. And as you'll see, there's a close relationship between the magical and psychic. So I was on a TV show a couple of years ago, and the interviewer asked, what is ESP? So I said, it is perception extended through space or time. Well, what does that mean, perception extended through space or time? Well, the words that we use are clairvoyance, precognition, and telepathy. The words are just descriptions of what the experiences are. They don't suggest that they're separate phenomena, but they're descriptions. And the same goes for mind-matter interactions. The word we use is psychokinesis, but again, these are placeholders as ways of describing the nature of the experiences. So she then asked, is there any scientific evidence for ESP? And my response was, yes, there's lots of evidence. So she immediately responded with, but some scientists insist that ESP is impossible. For example, Sean Carroll, a physicist at Caltech, says basically that everything is made of matter, including the brain. The mind is identical to the brain. The brain can't transcend space-time, so therefore ESP is impossible. That's the end of that story. Or here we have Steven Weinberg, a Nobel laureate physicist, who said, if there was anything to psychic phenomena, that would really be the discovery of the century. In fact, it would be more than that. It would overturn all the centuries of work since the birth of modern science. So these are common reactions to hearing about psychic experiences. There are things like it's impossible because it violates scientific law, or the reports are only made by ignorant or superstitious people. The reports are anecdotes, they're not controlled. The reports therefore deserve sarcasm and ridicule. And the scientific elite openly opposes journals that dare to publish positive articles. So this makes Grumpy Cat even more grumpier than usual. So I responded, well, they're talking about theoretical assumptions. The experimental evidence is very clear. Then why don't they know about this, she asked. And in 2 words, the answer is because of the scientific worldview that we're all trained in. That worldview is called materialism or reductive materialism. It assumes that at the bottom of everything, we're dealing with the physical world in terms of the way that physics describes it. And from that emerges chemistry, and from that emerges biology, and from that emerges psychology. And somehow magically at the top, you have consciousness, which means self-awareness. It's the act of being aware, because as far as we can tell, there's nothing aware in physics, chemistry, biology, or psychology. Consciousness, our self-awareness somehow must arise out of all of that. This gives the idea to philosophers that consciousness as an emergent system out of physicality is basically like zombies. Like we have the appearance of being living, aware creatures, but we're really not. We're more like mechanical systems. And so under that condition, the idea of psi or psychic phenomena, it's denied as impossible. And of course, the thing is that it's not reasonable to throw away materialism because it's extremely successful as a way of understanding the nature of the physical world. The problem arises that empirically, meaning laboratory tests, we know that these phenomena exist, so we're missing something. And as I told her then, that worldviews, especially the worldviews that scientists are trained in, are like blinders. They only let you see what you've been trained to see. Anything else becomes impossible or a mistake. So she asked, well, then what is the evidence? Well, I said, okay, we'll go to people who specialize in evaluating evidence, namely statisticians. Here's the presidential address for the American Statistical Association in 2016. The president said, that the data in support of precognition and possibly other related psychic phenomena are quite strong statistically and would be widely accepted if they pertain to something more mundane. Here's another example. This is 2018 in the flagship journal of the American Psychologist. This is the main journal of the American Psychological Association. So Edsel Cardinia is a professor at Lund University in Sweden, and he wrote, "The evidence for psi is comparable to that for established phenomena in psychology and other disciplines." As a result of that, there was another article published about a year later in American Psychologist called "Searching for the Impossible, Parapsychology's Elusive Quest." I won't bother to read this. I'll just say that the key phrases are that claims are made that cannot be true. The data have no existential value. Our conclusions are based on well understood scientific principles. And there has been literally no progress in establishing the existence of psychic phenomena for about 150 years. So that's like the mainstream response to the article saying, yeah, these things actually do exist. Well, that makes Grumpy Cat even grumpier. So for example, here's physicist Ernst Chladni, or Chadley. I don't know how you pronounce his name, but anyway, he was the physicist who said that occasionally rocks fall out of the sky. In other words, he was taking advantage of observations of meteorites and proposing that there's something out there in space. So these were the responses that he got. And you might recognize these because they're impossible because they violate scientific laws. The reports are made by ignorant people. It's based on anecdotes and so on. These same kinds of reactions happen again and again. And there are lots of examples throughout science where if somebody presents something which is considered an anomaly that is somehow challenging existing laws, the same reactions you see again and again. So why am I interested in psychic phenomena in particular? The first reason is that it's a major challenge to assumptions about the relationship between the brain and the mind. They're very commonly reported. It's perfectly amenable to scientific study. The study itself stimulates methodological advances, a very distinguished scientific history, and it's identical to magical practices, as you'll see in a bit. So first of all, how common are these experiences? So we asked members of IONS, where I work, the general population, and also scientists and engineers. We gave them a list of 25 different kinds of experiences that people report and asked, how many of these have you ever had? So among IONS members, 99% said they had at least one of the 25 experiences. And we didn't use any of the typical psychic terms. We just gave an experience like a feeling of connection from a mind to mind. So on average, 13 of the 25 experiences, that's how many people said on average. Among the general population, 94% of people said that they had these experiences, and on average, 8 of the 25. And our surprise was that scientists and engineers, 93%, and actually on average more, 9 out of 25 of the experiences that scientists and engineers report. Well, why is this? Because these experiences are common human experiences, and scientists and engineers actually are human. As far as the distinguished scientific history goes, we can go back to the founders of modern science, Francis Bacon, Isaac Newton, Galileo, Robert Boyle. What was their interest? Bacon wrote about methods of testing for telepathy and psychokinesis. Newton spent a lot more time writing about alchemy than he did about physics. Galileo specifically wrote about astrology. Robert Boyle wrote about clairvoyance. A little more into the present day, J.J. Thomson, a Nobel laureate, Marie Curie, a Nobel laureate, Alfred Russel Wallace, William Crookes, William James, all very famous people. Thomson did studies in telepathy. Marie Curie was interested in mediumship and attended seances, as did Alfred Russel Wallace, as did William Crookes, as did William James. Even closer to the present time, J. Edgar Hoover at Stanford University, Hans Berger, the inventor of the EEG, Charles Richet, a Nobel laureate, who was the first to use statistics in psychological experiments and applied the very first case to ESP tests. J.B. Rhine, of course, Gustav Fechner, Jack Parsons. So Coover created randomized double-blind trials to study clairvoyance and telepathy. Hans Berger developed the EEG because of an experience of telepathy with him and his sister. Charles Richet applied statistics to ESP tests. J.B. Rhine, of course, is well known, but was one of the first, maybe the first, to use meta-analysis to demonstrate repeatable effects among different experiments. Fechner wrote extensively about mind-matter interaction because he was interested in mysticism. And within the mystical view, mind and matter are basically two sides of the same coin. Jack Parsons, one of the key scientists at JPL, was a ceremonial magician, actually developed some of his rocketry ideas based on magic. So all of this is part of the history of real magic, which is not typically taught in the scientific curriculum. So one of the things about, as soon as I mention the word magic, what comes to mind is this. This is how magic is portrayed in fiction. And of course, anything in fiction is always going to be embellished. So when I'm talking about magic, you should take all of this movie type magic and set it aside for a moment. We're talking about these phenomena, but just not, of course, as strong as what is portrayed. So it's not fictional magic. It's not Harry Potter. It's not practical magic. It's not Magic Mike type of magic. It's not fake magic. It's not stage magic either. Magic is to the esoteric worldview as technology is to the scientific worldview. In other words, a worldview is a set of theories, a way of thinking about reality. The practical application of that worldview in today's world is technology. In the esoteric worldview, it's magic. So the three practices are divination, force of will, and theurgy. So divination is perception through space and time. Force of will is basically, we'd call it psychokinetic effects. And theurgy is communicating with spirits. So we can ask then, from a scientific perspective, does divination exist? Well, we're talking about, first of all, perception through space. So here's an example of remote viewing, which is perception through space. You take somebody and you ask them, describe where your friend is now. So this person then makes a sketch of what her impressions are. So the sketch has words like very open, very airy, lots of poles and construction, something like a fence, like looking at something that narrows, quiet and solitude. So these are four possible places where her friend could be. And earlier in the day, a random decision was made. One of those four places was selected, and so the friend went there. And when the friend was there, they took pictures of what it was like to be there. So now we come back to the lab. We give the remote viewer's impressions to a judge. I'm using Judge Judy here. And we show them four pictures of where the friend might have been. And the judge's idea is to match the impressions that were taken with the actual location. So Judge Judy would say, oh, it looks like it's this place. So you can see that this is a very simple hit or miss type of game. In this case, 1 in 4 chance of getting it right. So when you look at representative tests over many years from SORI International, SAIC, and Princeton, from the probabilities of these results, there's no question that these are real phenomena. People can do this task. And there are plenty of articles now written on these kinds of things. A more interesting question is remote viewing pragmatically useful? So this is part of the US government's program in remote viewing for psychic spying. So when you look at the program, at the time it was a top secret program at Fort Meade using psychic spying, 450 missions with 2,738 individual sessions. Well, who was using this? Well, so for example, the Army requested for 31 missions. The CIA requested 34 missions. Defense Intelligence, 122 missions. Joint Task Force, which is typically combinations of various Army and intelligence outfits, 172 missions. NSA, 17 missions. US Coast Guard, 23. What this tells us is if they did a couple of missions and the results they were getting back wasn't very good, they wouldn't come back again. So apparently the FBI and the DEA didn't have very good success. But some of these places had really good success. That's why they came back again and again for operational information that was usable by them. So to learn about this in great gory detail, there's 2 books I recommend. ESP Wars, East and West, which tells about the US and the Russian versions of remote viewing programs. And then a 4-volume series called the Stargate Archives, which is most of the original reports that were produced by the government program. But what about perception through time? So one way, there are many ways of looking at this kind of phenomenon, but one that I developed is called presentiment, where you take some kind of physiological measure, you make a random decision, and you either show calm pictures or emotional pictures, and you measure what is happening to physiology before, during, and after the picture. So here's a typical example of measuring before and after a stimulus. So the stimulus occurs here. This is the average of the physiology before and after seeing the stimulus. And here is the physiology before and after seeing an emotional stimulus. The difference then, this is what I'm calling a presentiment. There is evidence that even when the future is completely unknown, it's selected randomly, that people become more emotionally aroused before seeing the emotional pictures than before the calm pictures. So this has been done in many different areas of physiology now, including pupil dilation. So here's a setup where a subject is looking at pictures, which you can see at the top here, and it's tracking the size of her pupil in the bottom. And this study, like we see with skin conductance and other measures, their pupil has a different size, a different response before and during, and actually even after seeing emotional pictures than calm pictures. So this difference here is what we call a presentiment effect, and it's statistically speaking, there's no question that there is a big difference in the pupil size. So a few years ago, there was a publication in Frontiers in Psychology, which was a meta-analysis of, at that time, around 36 studies. This paper has been seen over 100,000 times, which is extremely unusual for any kind of scientific paper. It is more views than 99% of all of the articles, the millions and millions of articles published in the Frontier series of journals. Now there's about 48 or slightly more than 48 studies, and the results are still the same. There is basically no question. This meta-analysis, the overall result was 10 to the minus 12th, indicating that there is more physiological arousal before an unpredictable stimuli. Well, what about force of will? Does force of will exist? Well, the most common target are probabilistic systems. So here's an example of one very early one back from the 1980s at Princeton University. These are systems that just produce sequences of random events. Today, you can get an almost identical system on a USB stick, which is just as good as the older systems that had to be custom made. So at Princeton University, for many, many trials, they would have people aim high, namely to have the random system produce more 1 bits. And sure enough, over many trials, you track the results of those trials, it started deviating towards too many 1s. Same with too many 0s as the target. And then they, of course, had baselines, which fluctuated around 0. So this is a highly significant result. When I was at Princeton, Roger Nelson, a colleague of mine, and I did a meta-analysis of all of the studies that we could find in the literature at that time, including the ones from the PAIR lab. And at the time, there were about 800 relevant experiments. We found unequivocal effects in experimental conditions, chance results, and control conditions. So those were many, many replications of studies. So here I'm going to talk about some specific studies that we did on different systems. So I was interested in electrical plasma because it is so sensitive to electromagnetic and electrostatic effects. I figured it might be a good target. So what we did is we simply asked somebody to mentally concentrate on a plasma ball and try to move the streamers in a specified direction. We, of course, couldn't ask somebody to be close to the ball because otherwise they could influence it simply by proximity. So we put the ball inside an electromagnetically shielded chamber in front of a webcam and then brought the image of that outside the box and had the person look at the image and try to move the streamers around mentally. So under control conditions where nobody is the exact same setup, but nobody's mentally trying to change anything, these little boxes show statistically significant differences in the images that were being captured by the webcam during intention, trying to influence the system versus withdrawing mentally from the system. But again, no one was trying to do this, just looking at what happens when you run the system. And this is what we found during experimental conditions where people were trying to move the streamers to the right. So not only do you see movement towards the right, but there are many, many more statistically significant differences in the images when they were trying to move it to the right versus withdrawing their attention. So clearly something is going on in these with plasma, which was fun to see. Another example, we did a whole series of studies looking at what happens if you mentally try to influence food or drink. So we did an experiment involving chocolate, which was double-blind, randomized, placebo-controlled. We had a Buddhist monk and also a Mongolian shaman mentally bless pieces of chocolate, which you can see here, little dark pieces of chocolate, such that anybody who ate that particular chocolate would get an enhanced sense of energy, vigor, and well-being. So we recruited people to, of course, blindly. They didn't know they were getting the blessed chocolate. Others were getting the same thing, looked the same anyway, that was controlled, unblessed chocolate. They had to eat the chocolate over the course of a week on days Tuesday, Wednesday, and Thursday, but every day of the week they would record their mood. And so we were looking at, does the mood actually change when people are eating the blessed chocolate or the intentionally influenced chocolate versus the control? And in fact, we found that they did. So the mood was significantly better. This is presented in terms of mood disturbance. So the control condition, mood disturbance, was significantly higher on the last day of eating chocolate than on than when people getting the intentionally influenced chocolate. So these are 95% error bars. You can see then that eating the blessed chocolate both improved the mood and mood sustained, whereas it bounced back to baseline for people getting the controlled chocolate. So intention significantly improved mood, altering properties of chocolate. We did a similar thing involving mentally influenced tea, oolong tea. So we made a big batch of tea, separated it into two batches, had Buddhist monks bless the tea, again, to improve mood of anybody who drank it, put those tea into tiny little bottles, gave it out to 100 people in both conditions and double blind. And the results, again, were similar to the chocolate. People getting the blessed tea without knowing what they were drinking reported better mood. Now, this one is change in mood in a positive sense. So the blessed tea gave a significant rise in mood, and the untreated tea gave basically no change in mood. So intention significantly improved the mood-altering properties of tea, in this case, oolong tea that had caffeine in it. Well, what about a more objective measure? So we did a very similar experiment, but measured plant growth as a result. We used this plant called Arabidopsis thaliana because a lot is known about it, the genetics. Its full genome has been sequenced, so we know about the genetics of this plant. So again, we had Buddhist monks bless water, which was used to hydrate the seeds, and we also had control water. There's my colleague. This was all done in Taiwan. So this, again, double blind. The person handling the seed, hydrating the seed with the water had no idea of the difference between water A and water B. And then a number of measures were taken on the plants that were finally grown. So we're interested in one measure called hypocotyl, which is the difference from the roots to the top of the leaves. And at least on this one measure, we did this repeated 9 times with the same experiment 9 times, double blind. And the treated hypocotyl was significantly different than the control water hypocotyl. And in this case, a improved growth of seeds for this particular kind of seed, the hypocotyl would be smaller. It would be short and fat. And that's what we're looking for because that indicates a healthy plant. And the controls were not quite as short or fat. These are 95% confidence intervals, which is why the probability of this difference is 10 to the minus 14th. So intention significantly improved the growth of seeds, in this case, intention at water. If I have 5 hours, I can go through studies with photons, random events, water, food, wine, plants, cells, animals, human health, human behavior. The preponderance of the evidence across all of these targets show that force of will, in the magical sense, or psychokinesis, and in terms of psi research, it does work. It does, something happens. So people then ask, well, okay, let's say these psychic things or magic is real. How can it be real? This requires us to re-examine the foundations of science. In this case, we go all the way back to shamanism. We look at what did people think about the world from a shamanistic perspective. Well, we immediately bump into ideas like Hermeticism, Neoplatonism, the Kabbalah, alchemy, Gnosticism, yoga, the Vedas, Kashmir Shaivism, Buddhism. And then in the medieval times, the Freemasons, the Rosicrucians, Gurdjieff, Theosophy, the Knights Templar. This is all part of what's called the perennial philosophy, which is very simple. It says consciousness is fundamental. It's very different than materialism. In fact, it's the complete opposite of materialism. And the way to think of it then is that we see physics, chemistry, biology, psychology, and consciousness. Idealism says all of that is correct, except consciousness actually is more fundamental than physics. From this perspective, psychic phenomena, magic, mysticism, they're all completely acceptable because now consciousness comes before physics. It comes before concepts like space and time. In addition, consciousness now, from consciousness emerges physics, emerges chemistry, and so on. So it is not a mystery why consciousness is somehow found in biology and psychology, because it was there from the get-go. It was there from the beginning. Another way of looking at this, and I'm borrowing a few slides from John Hagelin, the physicist, is to think about how we think about and how we model the idea of matter. So it's a little bit like an iceberg. So above a certain level, like a visible level, matter we think of in terms of things like what we make with it, electronics, telecommunications, aerospace, lasers. And our models are classical mechanics, thermodynamics, statistical physics, and so on. So just below the level of what you can see with your eyes, at least very easily, we have nuclear physics, quantum physics, atomic physics. And below that, we start dealing with force fields and with matter fields. And below that, most physicists assume that there's some kind of a super unified field. All the laws of nature come out as something. Well, there's a parallel with the mind. The mind at the everyday level is conscious, but we're well aware that there's preconscious, subconscious, unconscious, and something goes all the way down. That's the assumption, at least within the contemplative world, that the mind does not stop at some point, it goes down. And if you're a meditator, you experience that. So up at the top here, we have common sense. Somewhere further down, we have psychic sense. Further down, we have the mystical sense. Below that, we don't even know what to call it. So here's an interesting third parallel about mathematics. So at the very top of mathematics are counting numbers, like the numbers on your fingers. Below that, we have slightly more abstract numbers like fractions, and then more abstract and more abstract and more abstract and continually abstract. And then algebra, which is kind of surface level operations on numbers, and then more abstract, more abstract, more abstract, and so on. We get down all the way down to things like gauge theory and set theory. They're extremely abstract operations on very abstract kinds of numbers, but they're necessary for us to devise descriptions like a super unified field, or perhaps related also to some pure consciousness unified field. So as we go down into matter and energy and down into mind, we become more and more abstract in terms of the tools that we have to describe what is happening. So we could say then that mathematics is basically a symbolic language. It's a language developed by the mind, which turns out to be extremely successful in describing things all the way down, way below what we can see, even with our instruments. And it goes all the way at the top to all the way in the bottom. What's interesting then is that this is very, very similar to what is said in the esoteric literature. Esoteric literature, including in this case the Kabbalah, say that reality is composed of symbols. And the emergence of the world, it comes about as a result of the language of these symbols. This is the basic of ceremonial magic. When you go to a grimoire, which is a book of spells, it's all about these symbolic terms that are used to create the world. So there's the connection between deep math, deep physics, deep mind, and magic. So it's a little like we're Alice pulling aside the curtain of reality. And you see this again and again now. First of all, is there an objective reality? Well, here we have an experiment showing that two observers experience different conflicting realities. Here's a blog in Scientific American, coming to grips with the implications of quantum mechanics. The question is no longer whether quantum theory is correct, but what it means. And that what it's basically saying is a primary role for mind and nature. Likewise, the leading books written by thought leaders in physics and quantum mechanics and mathematics and in neuroscience are all saying the same thing. They're saying that the fundamentals of reality is not matter and energy anymore. It's information, it's mathematics, it's consciousness. Even Christoph Koch, who's one of the leaders in neurosciences, is saying, like the idealists have always said, I believe that consciousness is a fundamental and elementary property of living matter. It can't be derived from anything else. You see now that university and professional presses like Columbia, Oxford, American Psychological Association, American Institute of Physics are publishing books now which are saying the same thing. There is something strange going on about the role of mind and consciousness in the physical world. To which the baby could say, well, so what? Why is this important? Well, it's important because the current scientific doctrine of materialism says we are machines made of meat. That's it. That's all we are. And we know how we treat machines. They have no meaning or purpose. We throw them away, and that's the end of it. Well, maybe we're machines made of meat, which is certainly true, but maybe there's something more going on. So this is a nice drawing by Alex Gray. There's something else happening. It's not just machines made of meat. And the bottom line then, both from the study of magic, study of psychic phenomena, virtually all of the esoteric traditions tell us again and again that separation is an illusion, that we have the appearance of being separate, but we're really not so separate after all. That means that we live in a fully entangled, fully interconnected reality. Why is this important to people interested in energy? Because you look at the lineage then from ancient esoteric lore to future science, and this is a shameless plug for my most recent book, Real Magic, which goes in all of this in detail. It says, because consciousness may be more fundamental than matter or energy, our very concept of energy, what we mean by it, seems to be headed toward a radical change. There may be no difference between consciousness and energy, or maybe they're two completely fundamental properties of reality, but coexist in some form. We don't know yet, but our ideas about what we think of energy is probably going to change. So I'm going to stop there, and then I'm going to answer questions. So I'll stop the recording.
Thank you, Dean. That was excellent. In fact, we're amazed at the content that you've portrayed in one lecture that really gives us an insight into your entire career. It's amazing in 45 minutes that we can see your entire life, at least your adult life, that is. So I give you great congratulations for that. What I was also going to ask you, if you don't mind me taking the initial question series of people that are on the chat box. I also was and still am a fan of the psychologist Carl Jung, J-U-N-G for the readers that don't know about him. And Carl Jung has lots of books. The collected works are a couple feet thick. He has one just on alchemy, for example. I'd say the dynamic psychology and dynamics of psychology is one of the most interesting in terms of the separation of matter and psyche. And he agrees with you 100% and gives lots of historical basis for the psyche being fundamentally underlying physical reality. So I just thought perhaps Carl Jung might be somebody you've already studied. I'm not sure if you reference him in your latest book, but I just was curious about your reaction to Carl Jung's work. And I think we have to unmute you, or could you unmute? In fact, I might have to invite you to unmute. Perhaps that's the next.
There we go.
There we go. Thank you.
Yeah, so I've read much of the work of Carl Jung. I'm particularly fond of of the book that he did with Wolfgang Pauli.
Yes.
Because Pauli, of course, is a physicist. He was the one that the other physicists developing quantum mechanics considered to be the smart one. So between Pauli and Jung, they had very interesting discussions about the nature of physicality and its relationship to the mind.
I have their book.
Yeah, Pauli and Jung. So that's where I've gotten some of my inspiration about why, even though it is definitely not part of mainstream physics today to talk about the possibility that consciousness is part of it, a lot of very well-known physicists have been very seriously interested in this idea, and you're beginning to see that it's slowly beginning to penetrate back into the mainstream.
Good point. See if I stop screen sharing, I think you'll take over the screen. There you go. So, and actually the other outgrowth of that is perhaps the basis of some of the more phenomenal performances that your supernormal book refers to, where people that believe and practice the esoteric disciplines you mentioned. Wim Hof is my latest fascination, standing out in extreme cold. He's been to Antarctic with just shorts on, sitting in lotus posture in the midst of a glacier. So these are people that perform tremendously, swimming the English Channel, for example, when doctors said, no, she's going to freeze and have, cardiac arrest, climbing rock faces for hours and hours without water. Wim Hof ran a half a marathon with no water in a desert, in a 100-degree desert. So the performances keep getting more and more phenomenal. And I wondered if this may become a mainstream science, at least for the military eventually.
Well, it is. I mean, it is slowly becoming a topic of study. It's always a bit tricky when you have a handful of people who can demonstrate these things.
Right.
Because it raises suspicions that they're doing a trick or something.
Right.
So many people now are practicing the Wim Hof method. There are more people who are involved in meditation and other forms of psychophysiological control. So as it becomes easier to find people who are able to demonstrate these things, then it is no longer an object of such skepticism. So that is happening. And we're trying to do it in the domain of psychic performance as well. As in any area, you find some people who are extremely talented, but they're looked upon with suspicion, and understandably so. So we're trying to expand our reach to find a lot of people who are quite good at these things. And this is where the internet is actually helping us, because we can have lots of people do these kinds of tests and then vet them for talent from afar.
Yeah. Have you studied meditators like the Transcendental Meditation group has? And have you found them to be more psychically able to perform in various tests?
We haven't, well, not formally, but in some of the experiments I've done, we've simply kept track of people who are meditators who are not meditators. And we generally find that the meditators do better. In this case, though, it's usually because, especially for mind-matter interaction studies, the instructions that you give to the subjects require that they focus their attention on something. So it's not too surprising that people who are trained with attention focusing, namely meditation, they do the task better because they're able to do it. Whereas a person who's not used to focusing their attention for very long we'll do the task for about 2 seconds and then start dreaming about hot fudge sundaes. Of course, that's not what we want them to do. So at this point, what we're seeing is, yes, meditators tend to do better, but we haven't found people who are able to demonstrate the cities on demand.
There you go.
Special yoga superpowers on demand. That, we haven't seen that yet.
I see. And actually, that's one of the related questions. Cities are in yoga traditions, according to one of the questions that come up in the chat window. Also, spoon bending within your realm of purview. The Jack Howe, perhaps. I used to know Jack Howe personally, and always think he deserves a book in his name just because he taught spoon bending, psychic spoon bending, and metal bending, half-inch rods, and so forth.
Well, so on spoon bending is a macroscopic psychokinetic effect. At least that's the claim. I've had a number of colleagues who would go to spoon bending parties and do interesting things. And I was never quite sure what to believe about it, because bending a spoon at the neck is not that difficult. It doesn't take that much force. Bending the bowl of a spoon, that's much more interesting, because
that's what I'm talking about. And then a half-inch steel rod
with your fingers, and even more so taking like a 1/4-inch rebar and bending it. That's not that easy, or aluminum bar. So I went to a spoon bending party. It was, I think it was around 2000 or 2001. And I was determined to watch somebody very close up who had previously bent the bowl of a large soup spoon. And so, because I thought, well, that would be interesting to see. So I was holding a soup spoon in the same way that this lady was. And it turned out that I ended up bending the bowl of a soup spoon in half.
Good for
and
you.
So that was a lot better than watching somebody else do it, because then I knew what it felt like.
Yeah, it gets soft all of a sudden. Yeah.
It felt like people describe. It's like it suddenly turned into taffy, and it was squishy, and it took basically no force to just squish it in half. Wow. And then it hardened up, and that's how it looks today. So I don't doubt that the phenomenon is real. The problem is that it's very, very difficult to get somebody to be able to do it on demand.
Yeah.
So it's virtually impossible to do this under laboratory conditions. What we can do is we can do metallurgy on the metal afterwards and see if we can figure out why it bent, or why did it become soft. But we can't get much further in terms of a scientific test unless we can figure out a way of making it happen when we want it to.
Well, one of the questions in the chat window refers to some Tibetan yogi that apparently is able to bend rebar into a knot. So if this person can connect you with the Tibetan yogi, would you be interested?
Yes.
Okay, that settles that question. Have you studied near-death experiences?
No, because it is primarily an anecdotal report.
Not on demand.
My specialty is laboratory study. So I'm always looking for someone who can demonstrate something, not only on demand, but in the form in which we want to study it. Because otherwise you don't have control over it. So the closest that anybody has come to control tests of near-death experience is Sam Parnia, who is in a number of surgical rooms in hospitals, I think around the world, is putting pictures that are facing upwards near the ceiling. So if the person is having an operation, typically they're doing something about the heart, they stop the heart, the person is essentially dead for a few minutes. If they float out of their body and are able to go up to the ceiling and look down on this little platform, they'll see a picture. So when they are resuscitated, they're asked, well, did you go out of your body? Did you see something? And after quite a few hundred, I think, episodes like this, there were not very many near-death experiences reported, and no one was able to report the picture. So that's a quasi-experiment. It is controlled, but so far there's no one has been able to report the picture. So since I'm not a medical person, that's not the kind of experiment that I can do, even though I think it's a nice experiment to try.
I came across some experiments with people who don't eat, literally have no food or water for extended periods of time. They've even been studied under laboratory and hospital conditions. I'm not sure if that reaches into the realm that would be noetic science.
Well, it's peripheral. You know, it has to do with exceptional human abilities.
Yeah.
I'm the editor of a journal, and we're going to publish a paper which goes into these cases in great gory detail.
Oh.
So there are a number of cases that were studied in hospitals. There are a number of reports of various types and different levels of observation, going all the way back and even before the Catholic saints,
Right.
many of whom became saints as a result of not eating or drinking for decades sometimes.
Right.
So for someone to become a saint, they of course had to withstand the devil's advocate, who was the professional skeptic arguing why they should not become a saint. And it needed quite a bit of evidence at that time. The type of evidence that the church would use is not exactly the same as what a scientist would use. It's more like a court of law.
Mm-hmm.
So is it a phenomenon that I think is worth studying? The answer is absolutely yes.
Mm-hmm.
It's possible that this could be done under better controlled conditions, because there's quite a few people who claim that they don't eat,
Yeah.
or that they eat at extremely low levels and don't seem to show an effect of it. Unfortunately, there's also some fraud associated with it.
Sure.
So the skepticism that one reads about is not for no reason. There are reasons to suspect that some of the people making these claims are delusional and some are fraudulent. Some of them are probably real too.
Mm-hmm. Well, our last question briefly is, are you aware of Dr. Alexander Parkhomov, whose work with the great Russian psychics in the Soviet era was publicized, I believe, and recorded in a book, Space, Earth, Human? I remember the Russians had psychic experiments, and they were even videotaped and broadcast on television.
Right. I don't know that name in particular, but I do know that at the same time that the US government was having our psychic spying program, that the Russians had a program at the same time, and actually continued after ours, and was funded to a much higher degree. Many more psychics were involved and scientists.
Sure. I even have, you probably have it too, Dr. Hal Puthoff's report on the CIA remote viewing program, which he claims he actually directed for a number of years.
Well,
So,
he not only claimed it, he did.
that's a good point. Nobody knew that, but
no, I knew that because I was part of the program and I could see Hal in his office. So
I see. Well, thank you for confirming that. I really appreciate it.
yeah.
Okay. Well, it looks like we're past our break time, and thank you very much. Do you have a contact information in case people want to email you directly?
Yeah, it's pretty easy. I'm Dean and I work at ION, so I'm dean@ions.org.
There you go. Thank you very much.
You're welcome.
Good luck to you. Now you have to reset. There you go. spotlighting. It looks like my video is working, but maybe not spotlighted yet. Perhaps. Well, if you can hear me, I think we're all set to introduce our next speaker. The spotlighting aspect, our co-host is still working on it. Okay, so welcome back to our conference on future energy. It's our 12th in the series. We are happy to present our next speaker. And what's interesting is that the background that he has, it's Paul Murad. He basically has a bachelor's degree in mechanical engineering from Brooklyn Polytech and a master's in astrophysics from New York University. And he worked on the Apollo programs, the space shuttle program at NASA in the 1960s. And then for almost 20 years, he was a private contractor working on tactical and strategic missile systems. So he did a lot of extra work even after that for a few decades on foreign technology topics, and also with the Pentagon as well. Some of the interesting conferences that he's been a chairperson for is the magnetohydrodynamics for the National Aerospace Plane back in 2001, and also the first International High Frequency Gravity Wave Conference in 2003, which we were able to get the proceedings of on CD. So if you're interested in gravity and that particular Gravity Wave Conference, IRI does sell the CD record of that proceedings. Overall, it seems that Paul has covered a lot of advanced space propulsion, advanced energy, and gravitic concepts, and also presented different technical disciplines with 70 technical papers and also written 10 novels. Recently, with the Morningstar company that he's involved in, as well as Kepler Aerospace, he's been exploring the Morningstar energy box, as he calls it, which is a reproduction of the John Searle device in a single ring. So we give him lots of credit for following up on what the Russians and many other investigators have done to attempt to reproduce what Searle claims to have done with rotating magnets. So without further ado, I'll start the recorded presentation by Paul Murad. And I'm not sure if I have the correct settings. Let's see if I can share screen again and catch the right one. Okay, that should do it. And here's Paul.
Okay, we're at the 12th Conference on Future Energy, and our next speaker has a bachelor's from Brooklyn Polytech and master's in astrophysics degree from New York University. And he's worked on the Apollo space shuttle programs, NASA, and employed as a contractor for over 18 years on strategic missile systems and tactical work with the government. Interestingly enough, he's also been a chairman for various technical conferences, including magnetohydrodynamics for National Aerospace Plane and the High Frequency Wave Conference, and also STAFE, the Space Technology and Applications International Forum. He's also contributed to one of my books, The Future of Energy. And without further ado, speaking on the topic of gravitation as a rotational or vorticity field, please welcome Paul Murad.
Thank you very much. Next slide, please. Basically, anomalies and enigmas lead us pathways to discovery. In other words, when we find errors, we need to learn something along the way. Well, if you look at various gravitational laws, there are some problems. For example, Newton and Winterberg cannot produce gravity waves. Jeffremenko's model can, because he introduces a rotational field. Why does he do this? We'll discuss some of that. And there are other models that go further that improve Jeffremenko's model by leaving out cogravity. Next, please. One of the approaches to do this is to look at the conservation equation for continuity. And this leads us some insights into why you need to convert gravitational waves into a Newtonian field. Moreover, we look at a model on Winterberg and make an improvement on his model to account for some certainties, some anomalies, where gravity does not satisfy 1 over r squared, but ends up with a constant value. We also will discuss some issues about neutron stars, and finally, a black hole model that we're suggesting looks like a neutron star, but it's enclosed by a Faraday cage. And when energy gets built up, it injects a jet, and turns out there's only one jet that comes out. So there's some very interesting points that we need to look at. Next, please. In another analysis, I've looked at Maxwell's equations, and there are ways to end up with irrotational fields and no waves in Maxwell equations. When you go through the equations, there's a way of introducing time, and this implies that you need an ether or a Dirac sea for characteristic waves. Now the question is, do I need the same thing for gravitational waves? There are great things about Newtonian's gravitation. It works for satellites, it works for planets, but it's all in the near term. There are some flaws. We need to look at it. Now, either Einstein with gravitational waves is telling the truth, or Newton with no gravitational waves is telling the truth. Somebody must be lying. We need to find out. We're going to cover some terms that continue. Some of this will be based upon some previous analysis that we did last year. Next, please. One of the things that bothers me is when you have a red giant that collapses with a supernova. If the weight is below a certain limit, I get a neutron star. If it's above a certain limit, I get a black hole. How do you do this? It's two different things. And can we learn something about gravitation as well as the effect of spin and how that influences these models? Next, please. Can we characterize some different models? We intend to do that. Are some models proven? Well, some of them are. Can we change these models? Absolutely. And we need to have something about a model that includes gravity waves if we believe Einstein. Is this worth discussing? Obviously, yes. As I mentioned, Newton and Winterberg's model is irrotational, does not generate gravitational waves. Jeffermenko copies gravity using Maxwell's equations, where gravity is electric fields and co-gravity is a magnetic field. There are ways around this, and we have to look at it. If indeed there's a way of looking at this, we can find out if Einstein is telling the truth or did he lie. Next, please. All right, this is a table that I gave out previously. If you look in the right-hand corner, you see del squared phi equals 4 pi g. And if you look one step below that, you have del squared phi equals minus 2 omega squared. Those are elliptical partial differential equations. No characteristic waves. But the other ones all have characteristic waves. We have wave equations, d squared g dt squared minus del squared g. Those are wave equations. That'll produce gravity waves. Why do they work? Well, these models produce a curl term, and they interject time into the equation. Now, when we talk about gravitational currents, what does that mean? That's something is yet to be determined. And we're talking about, if we look at the last model, we make a simpler model where we're looking at the time change of current and of gravity. How do we interject time with gravity? Next, please. Well, that's one of the enigmas we need to look at, as well as others. For example, when you look at the microwave cosmic background radiation, you have 2.7 degrees. What's going on? 2.7 degrees, that implies energy. Energy implies mass. Mass is there, that implies gravity. Gee, what does that mean? Do we see that anywhere? Next, please. Well, the Milky Way has a lot of things to learn about, and we should look at this and try to understand how all these stars interact with each other. Next, please. Let's take a look at a galaxy, a spiral galaxy. Next, please. The Moon approach looked at stars in the spiral arms of galaxies, and something very unusual happened. Next view graph, please. He ends up with two curves. One is a lower curve, which he used when he's using Newtonian gravity, and the upper one is one that he sees in terms of data, where he's looking at velocity of these stars and the distance. And the first question you have is, this difference indicates there's a heck of a lot of mass in there. And how do I generate gravity to do that? What's going on here? Now, the common approaches say dark matter exists, but there could be other approaches as well. Next, please.
But this is the velocity graph?
Yep.
Okay, just to clarify for people.
Okay. Well, basically, if we assume V equals the square root of RG based upon units, we could say certain things. Let G satisfy 1 over R squared, which is Newtonian. You end up with 1 over the square root of R. That's the lower curve after a certain distance. If you let G a constant, then you end up with the square root of R, and that's the upper curve. So Moon tends to suggest that out there, you end up with something that looks like the square root of R. Next, please. Okay, if there's a constant value out there to do this, do we have any other evidence? Well, we have that with with the Pioneer 10 and 11 spacecraft missions. We're going to talk about that a little later on, where they result with a gravity, a constant value. In other words, instead of going over 1 over R squared, you go into a constant gravity, and it's like 10 to the minus 8. And if you look at the next view graph, please. If you look at the Oumuamua, you have something like 10 to the minus 4. Okay, if this is a factor here where gravity does not vanish infinitely, can we make an accounting for it? Can we go back, please? If we look at the Winterberg model, we are considering rotation in a neutron star. And what can we learn about this? Next, please. Well, I did an analysis last year, and we end up with certain results. Next, please. The results are that I don't know how to run this gravity law. So I looked at these terms as exponential terms, as well as source functions that will produce gravity potentials and gravities. And the question is, where are these gravity models end up with a constant at R equals infinity? Next, please. So what I did is I looked at the first equation, which satisfying del squared phi equals FR. When f of phi is equal to omega squared, that's Winterberg's model. Well, my feeling is that the rotational effect doesn't go out to infinity. It has to decay. So let's put a time, not a time, but a distance decay, and put that in there. And lo and behold, when we back off the function for gravity, we end up with R to the 1 minus 2n, or if n is equal to 1/2, we have a situation where you're generating gravity and it ends up with a constant value. And that was the second table, on the table, the second value we had. So that gives us an idea of what to look for a model for modifying the Winterberg model. Now, what does this mean about rotation? You could assume that the rotation ends when you end up the neutron star, which is insignificant, but I think it means more than that. If you look at the first table, first picture, it's from the Pioneer effects, where you're looking at the magnetic field from the sun to the earth, and then all the way out to Jupiter. It rotates once a month. If you look at a neutron star in the lower left side, you have the star rotating anywhere from 10 to 600 times a second, not once a month, but per second. So you're generating a lot of magnetic fields out there. By Maxwell's equations, you got to generate electric fields, and this might generate gravity. So you need that omega term out there. Next, please. All right, let's look at this conservation law. We're looking at the change of the source term and a gradient on the current. Again, what does a gravitational current mean? Hard to say. Let's integrate that equation as a function of time. We end up with a constant, not a constant, but we end up with a steady state term. Let's keep that in there. And when you put that in the original expression for Newtonian with gamma counted for relativity, you end up with what's going on. And finally, you back out G, and you end up with the term that includes an integral for the current as a function of time, a steady state value, a constant, CG. Well, maybe that's this constant value we're talking about, and something we don't know anything about. It's f of g of t, just a function of time. nothing else. That could be a Dirac delta, a Dirac C, who knows? Next, please. So when you go through this, you try to fool around with these equations. You could change that term into G caret to be that steady state gravitational effect. And you have to take a curl term. Well, if you take a curl term, if it disappears, then we have a irrotational field. There's no gravity waves. So J of S got to be there, and G caret's got to be there. So sticking another curl term in there. Next view graph, please. And do some manipulations. And as you go through this, you find out that certain terms appear, but they disappear. And you finally end up on the bottom with minus del squared G equals 4 pi G, so on. You can argue you're going to get that directly by using the gradient and the terms, but then you have an additional term in there, del cross G. Now, if G caret is a function of R, that should disappear, but you never know. Next, please. Well, what about the other side of the equation? Let's take time derivatives. When we take the second derivative, the G caret term, because it's steady state, disappears. And when you combine them now, you have a different gravitational wave equation. You've got the characteristics, a source term, the curl of the curl, and you have a function where current varies as a function of time, and another factor that's a function of time yet to be determined. Well, we've worked through this with Newtonian gravitation, so it looks like neither Einstein nor Newton lied. They're both telling the truth. Next, please. Let's carry this a step further. Let's assume the source term is equal to a separable time factor and a steady state value. And the same thing holds for the current. When you put this into the conservation equation and you do your manipulations, you end up with a Helmholtz equation that gives you an idea of the steady state source term. Next, please. Well, let's carry that a little further. Let's allow the body to rotate. Let's all allow the current to rotate. And when you put that into the conservation equation, and you do all the manipulation, it turns out the effects of the current is insignificant. But for the Helmholtz equation, you are driven by the rotation. Alpha is negative, so it's positive. So what's happening as spin goes, this charge density accumulates and increases over time. Next, please. Let's go a step further and change that value to beta omega squared. And lo and behold, this equation looks quite close to what Winterberg's suggesting. That's interesting. Next, please. All right, I mentioned this thing about Pioneer 10 and 11. They're spacecraft that have been there for a long time, and they keep going. Next, please. One went to the left, one went to the right. They went past the system. They're in the Oort cloud. They keep on going. Next, please. But they have a problem with their trajectory. It turns out that gravity indeed becomes a constant value above Uranus. And it's like I said earlier, 10 to the minus 8. Next view graph. As I mentioned, the same thing with Oumuamua. As it came into our solar system, it generated, it had undergone a gravitational attraction of like 10 to the minus 4, a constant value. So that between these two and Mund, there's a factor here where gravity does not vanish, like 1 over r squared at infinity. Next, please. When you look at the continuum, the space-time continuum, the deflection represents gravity. Well, there's our sun as an example. A white dwarf generates more gravity. A neutron generates a heck of a lot, but a black hole has a singularity. How do I go from the neutron star to the black hole? It's amazing. Next, please. Well, Paul Laviolette came out with a model on the pulsars, and the conventional wisdom is the neutron star lighthouse model, and it came about due to a burnt out star after a supernova, and there's a bunch of neutrons together that are forming crystals that are increasing the density and going on from there, and so on. And he looked at some signals and pulses that come out from this. We're talking about signals that come out anywhere from 600 times a second. And it's repeatable and it's extremely accurate. Next, please. But he comes up with some numbers that says there's pulse drifts. There are amplitude modulation effects. There are mode switching. What's going on? Now, I don't think he says this about all neutron stars, but this is some of the data that was out there. What does this mean? Next, please. Well, like I said, pulsars are very accurate, and we need to know this if we're going to go to cislunar and cis-Martian flights. So we better get used to it. Next, please. One of the assumptions is that neutron star is assumed to be a perfect sphere. What if the implosion is not even or uneven? We need to look at the exterior boundaries of the supernova to determine the size or the shape of the neutron star. And if it's irregular, there's got to be an electron gas over the surface of it. It's going to generate vortices at certain locations on the neutron star. And if this occurs, I will see things happen to the waveform. They'll end up with drifts and so on. Next, please. Well, here's a lighthouse model. It rotates around an axis. It sends out a beam of electromagnetic energy, and it sweeps over, and we see it on the Earth. If you look at the graph on the lower left side, there's the Earth going around the sun. It takes about a year to do that in one orbit. But for the pulsar, in that footprint shown there, it does that in a week. So that gives you a feeling for the difference in the gravitational attraction. Next, please. Here's some supernovas. Look at it. The one on the right side, that looks like I'll get a spherical neutron star. But on the left side, I don't know. On the lower left side, all bets are off. This might be ovaloid. God knows what it looks like. And that's the way to look at the neutron star.
The Crab Nebula, right?
Next, please. Here's some more to look at. Notice some are near spherical with hiccups. What we need to do is look at each neutron star and look at the differences in the waveform. Next, please. Okay, the other point is that this is being collapsed by a red giant star. But red giant stars, or any stars, do not have singular poles. They have multiple poles. Well, if it's collapsing, how does it come out with a single pole in a neutron star? Something's wrong. Next view graph, please. This shows you, for example, the magnetic field on the sun, a model. It's all over the place. Next, please. So what do? Well, finally, somebody put some sense together, and the model is on the right side, lower right side, for a magnetic field on a neutron star. In other words, there should not be a single beam coming out of a neutron star, but many beams. And we can't see it because we're on the Earth and we're only at one point. Next, please. In a previous model, I looked at the gradient, the curl of the current as driving the source term. Well, when you look at this, for example, with Winterberg's model, the equation becomes entirely difficult to deal with. And the bottom line, what I found out from this analysis was that the del cross J term isn't even part of the equation. So it's just something to keep on going. Next, please. All right, remember what we said about the pulsar, that this omega squared effect is there. It increases the density, and it builds up and builds up and builds up and so on. Next, please. Let's talk about a black hole. Well, a black hole has larger mass. Novikov says nothing leaves a black hole, which means no electric and magnetic fields will leave, no visible fields leave, which implies if anything does leave, it's got to move faster than the speed of light. But I have to worry about Hawking radiation. Well, if I talk about thermal radiation, it moves at the speed of light. I won't see it. What's going on? Well, jets exist. All right. People tell me that the jet is generated from the debris off the accretion disk. I don't believe this because the accretion disk material are balanced between the centrifugal forces and the gravitational attraction on the black hole. And it's angular momentum, and all of a sudden it's squirting out the angle, the axis of rotation. That doesn't sound good to me. So it's got to come out of the black hole itself. And it violates the factor that we might be moving faster than the speed of light. Next, please. Where does this jet come from? Well, if we look at a model, we talked about the neutron star model we talked about, put it in the Faraday cage. And here it's just building up with this rotation over and over and over, like a capacitor that you're charging it up and up and up. And sooner or later, it discharges. And when it does that, it generates a jet. Okay, but there's something else. The jet doesn't come out both ways. It comes out one way. Well, that must mean that this model that we have must also be a monopole, which adds another complication to this thing about a black hole. Next, please. Next. All right, here's a typical conventional wisdom viewpoint of a black hole. The jet's out there, the accretion disk. And in this case, somebody said, well, is the magnetic field around the black hole? No, that's not going to happen. Next, please. Here's a black hole that we have in the picture, and God knows what this means. Next, please. Again, one thing about the jets are the appearance of shocks occur, like gas dynamic shocks, which is kind of strange. And next one, please. Again, we have on the left, conventional wisdom side of what's going on with the jet, both sides. But on the right, in the upper left side, that's the black hole, and there's the jet. One jet. Notice that it has shocks. There's no other jet. Next one, please. Here's another one. Where's the other jet? Is it going in another dimension? Who knows? Your guess is as good as mine. Next, please. Again, there's one jet coming out of one side of the black hole. Next, please. And then unfortunately, you don't get good resolution. Next one, please. But we need to look at this. One jet coming out of a black hole. Wow. Next, please. All right, let's look at a gravitational law. Apparently we screwed something up with this, but then that's not too bad. What we end up with is G is equal to G, a perturbation function. And then we account for 1 over R, which is Newtonian. The alpha R is the terms that we got from the pioneer effects. So the perturbation function satisfies the wave equation that we showed before, and all the terms are there. And again, like I said, you have a source term, you have a time-dependent current, and then you have the second derivative of f of g of t, yet to be determined. So there are some enigmas here that we still need to discuss. Next, please. All right, what does this all mean? Well, we need to have rotational fields to produce gravity waves. We can do that Newtonian gravitation, as I showed you in this effort. This is similar to some efforts regarding Maxwell's equations with electric and magnetic fields. The Helmholtz equations give us some insights that it tends to amplify sources terms based upon rotation. We identified a new model of Winterberg's gravitational model that accounts for this factor that we see that gravity can turn into a constant, similar to what we see with the Pioneer spacecraft. Next, please. And that these results also satisfy some situations out of Mund. Now, neutron stars are quite complex. They're not perfectly spherical. We have to look at the boundary of the supernova. Next, please. And when we look at black holes, maybe the model here is that we have a neutron star and it's covered by a Faraday cage. And it too is built up with this rotation. And as this rotation continues and continues and continues, the source term explodes, it ejects some mass. And maybe this is Hawking radiation, could be. But the mass comes out of a single jet, at least in the black holes that I've seen. Next, please. Which implies that I have a monopole. Well, Tom recently showed me this figure of a new star where there are swirling jets in the plasma. And it turns out that sooner or later, the jet with all this spin, will become a planet. In other words, spin is required to start the formation of a planet, and gravity as well. I think that's rather amazing. Next, please. Well, where do we go? As far as I'm concerned, I like the neutron star model, but I'd like to figure out how you can build a black hole by putting a Faraday cage on a neutron star. And that's where I intend to go. Are there any questions?
Yes, lots of questions. I don't know where to start because your equation derivation would eventually get to answering the time derivative, variable, and give us some understanding of that f of t. That's my first question. So do you have any speculation about what f of t indicates?
Well, all I can say is that maybe it's from the ether.
Is it a gravitational wave?
It may be. It may be they contribute the constituents to end up with gravitational waves. And if that's the case, where's it coming from? The CG, I can argue with, hey, I think I know where that's coming from. But, it falls out of some of the equations. And in one case that I showed, it doesn't. Then you have to ask what's going on. But the other part of the problem is we don't know that much about gravitational currents. We don't know much about the effects of gravity as a function of time. And we need to know these things. Obviously, if we have a rotating Earth with the core moving around, that has current moving around, that has a source term moving around, the Earth should generate gravitational waves. Okay. Can we do that for a propulsion system? That is the $64,000 question.
Right. But at least you have an equation that indicates there is some wave. It's a wave equation format. That's what you concluded, right?
Yep.
And that's quite exciting. I mean, this is a publishable paper that you just outlined, which is, I hope to see it in a journal soon.
I will send you a copy of the paper so you put it in your next book.
Oh, well, I mean, it belongs to a good journal. I remember Mendel Sachs used to publish in I think it was speculation, not a speculation journal, but there was a gravitational journal that he liked and had many of his relativistic general relativity papers in there. But anyways, so you have some research that still can be done on the f of t for term, but the other big question perhaps is, have you been able to relate any of your concluding equational variables to actual data? For example, the constant gravitational force from the Pioneer.
No, I haven't done any of that yet.
Because that would be exciting to have, experimental data confirm what you theoretically predict.
I'm looking at other problems, unfortunately.
Oh, okay. Okay. Has any of this helped you understand the Searle device, which you call the Morningstar?
Yes, the Helmholtz equation. I never expected that effect. And
clarify, what's the Helmholtz equation? Because I think
that's where that del squared phi is equal to something else that seems to be amplifying itself. Oh. When I spoke to you about the energy box the last time, I mentioned that I put some crystals in there.
Right.
And when I rotated at steady state to warm the whole system, I was used to running it for 4 or 5 minutes before I put the crystal in there. No problem, over the years. And all of a sudden, this thing works for about one or 2 minutes, and it gets locked up, which meant that somehow I was building a charge up on the crystals, and that was affecting the magnetic fields within the energy box. And it was building so much mass and so much, not mass, but so much magnetic field, or maybe gravitation for all I know, that the machine used to work. I had a 1 horsepower motor on there. When we did this earlier, we had a 6 horsepower motor and it worked fine. So there was a constraint And I think that's because of that Helmholtz equation. That del squared phi is equal to something, and times phi, and something else maybe. So maybe that helps. That spin factor in terms of what's going on with the rest of the star systems generating gravity in a low value, that to me, I find kind of intriguing. And now the other question is, like I said to you earlier, how do we use this from a propulsion perspective?
Right. And we're looking to you for the answer to that question.
To be determined.
No, come on, you can speculate. It's okay.
To be determined.
Well, if you had unlimited power, for example, say one of the conversion devices that we're working on in free energy actually gave you, gigawatts or zigawatts or whatever they call it, beyond expectation, that sufficient amount of energy, maybe according to some of the great gravitational, electromagnetic gravitational journal articles I've seen, including Teller. Edward Teller wrote one, describing electromagnetic
well,
gravity.
I sort of like to, I like to favor the Potter model.
Okay, yeah, I like the
with the spinning magnetic fields.
Right.
And I'm seeing more and more pictures about these triangle vehicles with 3 spheres or 4 spheres on it.
Yep.
And the spinning effect somehow implies that there's somehow you're generating gravitational effects.
In one direction.
Maybe, maybe not.
That's what your jets seem to see.
If I had my druthers, I'd love to make one of those Potter devices. And in another area, I'm trying to put together a monopole. And we're yet to determine what's going to happen.
And is there stuff that Paul Lander is doing that you kind of scratch your head about?
No, no one has touched on me about the subject.
Okay, because there are electromagnetic anomalies out there, even the Manellis device with magnetic ferrites and so forth. But,
well, obviously everything depends upon funding.
That's true. Well, there's trillions of dollars out there. The government's arguing 2 trillion or 3 trillion. Oh.
Only if you have an illness or you can cure the illness.
Then, the sky is the limit. Yeah. Well, these are exciting graphs. I thought that this particular picture of the planetary formation, which, by the way, is actually right there. That's where the planet article I read. And the issue of it rotating, why do you think the rotation even begins? Is it because gravity itself contains that angular momentum?
Wow. I would look at this the other way as saying that somehow the spin started the effect and created the gravitation rather than the gravitation created the spin. But that's, like I said, you gave me that paper just a few hours earlier, and I didn't look through the paper, I just looked at the figures. That's hard to say if it was cause or effect and a cause.
Yeah.
I would suspect the spin is going to generate gravitation. Now, the question here is you're dealing with such hot gases in there,
right?
Hot plasma, that could be past a certain threshold to create some effects that we just don't know. And it's going to continue. And where does it go? Well, every star you see, every planet you see is rotating.
Yeah. And
in other words,
around it revolving. Yeah.
And I think that's what the rotation started the process, and it continues. Yeah. And if anything, once you form the body, maybe it starts decaying a little. I don't know. Hard to tell.
Well, even galaxies, a lot of, I don't know what the ratio of globular clusters versus spiral galaxies are, but I seem to see a lot of spiral galaxies out there, and they're all rotating too. Some of them even faster than they're supposed to.
That's something We need to look at those things.
Minor detail. Where's that dark matter that's missing?
Well, I don't think anyone's found any dark matter. My feeling is that all this rotation on the stars is generating this constant value that we see. And like I said, this is from the Moon effect as well as the Pioneer effects and Omaba. And maybe we should just, the thing is, you're dealing with angular momentum, and somehow there's this linear momentum effect, and we can't put our hands on that.
Yeah.
And that's like trying to understand what a gravitational current is.
Right.
How is it? Is it a bunch of mass moving at a constant velocity? Or does it involve electric and magnetic fields, or what? We really don't have a good, comfortable feeling about that. And we should try and find out what's going on.
Sure.
Or at least come up with some postulations and at least throw it out there, see if anyone accepts it or somebody denies to it. And the science method more or less says, hey, either we go with it or we don't, or we find another theory.
Sure.
And I think with more and more data based upon the Moore's law, where we double everything every 11 months, we're going to get more and more information and more insights. And we're going to have to change everything that we know to understand the new anomalies and the new enigmas that we see.
Sure. And eventually we'll see how to produce some propulsion, some artificial gravity. Yeah.
Yes, absolutely.
Well, we're looking to you for answers, and we hope that the Kepler Aerospace Company will be the first one to get the Nobel Prize on gravity production.
Thank you, Tom, and I appreciate all your help and confidence in all of this.
Thank you too, and let's keep in touch.
Will do, absolutely.
Well, we're really happy to have Paul join us, have had Paul join us with this very seminal presentation on gravitation as a rotational force. Of course, leaves more questions to be answered than answers the questions already out there, but it's also helpful to know of Paul's illustrious career in the government, and of course the military as well. So he's really tried his best to do theoretical physics whenever called upon to do so. And of course, this is another example of his expertise. So we're going to take about a 10-minute break right now, and then we'll be starting our last presentation at 5 o'clock Eastern with Colonel Eric Fell. Thanks for joining us. All right. Welcome back, everybody, to our 12th Conference on Future Energy. This is an exciting conference, and we've had some illustrious speakers, and our next speaker is no exception. Colonel Eric Felt is our last speaker of the day. He has a PhD in electrical engineering and the commander of the Phillips Research Site and director of the Air Force Research Lab Space Vehicles Directorate at Kirtland Air Force Base in New Mexico. We actually invited him because we thought we were going to hold it in Albuquerque and it'd be just a drive down the street to attend. But luckily through Zoom, we've been fortunate to still have him join us. So you didn't have to drive all the way to Washington, D.C. Colonel Felt also leads a team of 1,080 military, civilian, and on-site contractors who comprise the nation's center of excellence for military space science and technology, research and development, as well as advanced technologies, integration, and demonstration. And he focuses on the Air Force space missions, communications, position, navigation and timing, and missile warning and space situational awareness, and of course, defense counter space. He points out that he received his commission at Duke University, Air Force Reserve Officer Training Corps, and served active duty after completing a master's in science and a doctorate degree in electrical engineering. And he's been a graduate of the U.S. Air Force Test Pilot School, as well as being involved in various program and staff assignments. And he served as the senior material leader of the Joint Mission Division with the Intercontinental Ballistic Missile Systems Directorate in Utah. So speaking on the topic of space solar power, which is a hobby and a special interest of mine, space solar power incremental demonstration and research, please welcome Colonel Eric Felt.
All right, good afternoon, power enthusiasts, and it is wonderful to be able to talk to you today. I'm Colonel Eric Felt. I'm the director of the Air Force Research Lab Space Vehicles Directorate. I think of myself primarily as a space enthusiast, but I'm here to talk to you today because there is now a very exciting intersection between power and space. And so we have a project underway that we call SPIDER, the Space Solar Power Incremental Demonstrations and Research Project. And it is all about how to beam power from space. And I hope this can be a future part of our energy for our nation and for our world. And so that's why I wanted to be sure to talk to you today. So my mission at the Air Force Research Lab is to develop war-winning, game-changing technologies for space vehicles, for satellites. And we've been doing that mission for decades. We have made tremendous advancements in the capabilities of satellites over that time. I often say that we have made small sats act like big sats, and that's changing the world. And that is a very exciting mission. What we have seen recently is that the pace of technical innovation has accelerated even more than it was before. And I think that's happening for three reasons, really. One is that we've got a lot of commercial companies involved. You know, the government, commercial companies are now doing 80% of the investment in space research and development. Companies like SpaceX and Blue Origin and things like that. So that's awesome. They go a lot faster than the government and they have more resources at their disposal. So there's all this commercial activity going on. You've got a threat out there. You've got enemies and peer competitors that are trying to out-innovate us in every technology area, including in space. And so that has spurred us to innovate faster. And you've got a government that, our own government, that has noticed these things and cares about these things and is trying to keep us ahead so we can deter conflict in all domains. And so things like standing up the Space Force are a part of that third reason as to why the pace of technology innovation has gone up so quickly. And so all those things have come together to make this idea that we're going to talk to you about today, which is not a new idea at all, but it's finally technically feasible. And if I have to leave you with anything, that's what we have discovered recently, and that we're super excited to actually demonstrate, is that finally this idea from decades ago is now achievable, and we think that there are no technical roadblocks to actually beaming power from space. And that's what we're trying to show with the SPIDER project. We can move to slide 2. We can see the basic diagram of what we are attempting to accomplish with the Space Solar Power Initiative. It was a new start for us just last year when we were finally able to get some funding to go after this. And the picture over there really describes what we're trying to do. It's like we take solar energy, convert it directly into RF energy, and then beam that wherever you want. So it's power on demand. That is the basic operating concept of how you can do this. We are not striving to be the most efficient way to provide power, at least not initially, but there's great value in the power on demand concept because sometimes there's no other way to get the power where you want the power. And so that's all meant to be captured in the picture here. And this was this is now actually the largest program within my directorate. And we didn't even have this program 2 years ago. So it has very quickly come to us as this, again, those three forces kind of came together to make us realize that this was an exciting opportunity to go mature this technology. And then the programmatic responsibility was given to us to go show whether this is possible, or if it isn't, fail fast and let us know why. So that's how Space Solar Power Initiative got started. And this was less than 2 years ago when we first got involved in this. So our role, if you move to slide 3, you can see that we established the project. The culmination of the project is going to be an on-orbit demonstration that shows the basic feasibility of the concept. It turns out that you're going to need a very large solar blanket in space to beam a significant amount of power, and that's okay. We are not going to do that as our first goal. That would be too big of a leap. But what we're going to do is incrementally mature the technologies that we need to be able to eventually get to the goal of, as it says there, power a forward operating base with about 1,000 kilowatts. So that's something that's significant, but not a huge end all be all unachievable goal. And so the main process we've gone through over the past 2 years is one of what I call systems engineering, or decomposing the problem, where if you've got that vision that you need to be able to beam this solar power to a forward operating base, you then have to figure out how to do it. And what are the technical challenges to get there? And then decomposing all of those engineering challenges into small bite-sized pieces that can be digested. And that's exactly what we've done here with my team. So that has led us to this series of incremental demonstrations that we've talked about. Now, it's all based on what we call this solar to RF sandwich module. And let me show you what this looks like. This is a small piece of the module. And what you will find is that on one side, you're going to have solar cells that can collect the energy from the sun. And on the other side, you're going to have RF beaming microwave chips that can then beam the power wherever you want. And so the idea is that this whole structure will shift and as you determine where you want to be able to beam the power and where the solar power is going to come in on the one side. That is the key technology to make this possible, which was not possible 10 or 20 years ago when these ideas were first envisioned. So that's what we mean by the sandwich module, and then incrementally scaling up from this to 10,000 square meters of this up in space is the real technical challenge over the next decade that we'll be working on. If you move to slide 4, we can talk again about, why is this now possible? So what are some of the recent technology developments? I think this is really interesting, but first of all, there's a issue of mass efficiency and deployable structures. When you're talking about a 1,000 square meter structure, that's not something you're going to be able to just build on the ground and launch like we do with our current satellites. You're going to need to have ways to fold it up, to deploy it on space, to do it in a very mass efficient way. I talked earlier about, hey, how do you make small satellites act like big satellites? This is that on steroids. So, how do you take this really tiny structure and make it, when it gets onto space, act like a very large structure in terms of its capability. Increased efficiency of the modern electronics. I mentioned that our goal is not to be the cheapest way to deliver power, and that's for sure, but we have to be able to deliver power efficiently enough that it's actually a feasible concept to do this. And so you have to get the efficiency of the solar cells high enough to make this possible. You have to get the efficiency of the RF modules high enough that you can make this technically possible. Those incremental improvements have only recently reached the point where we think this is actually a viable concept. In addition to the efficiency of the solar cells, you need to work on their mass and their efficiency to get those down to a producible, mass producible quantity if you're going to be building this massive amount of solar cells and then launching them into space. That also wasn't really possible 10 or 20 years ago. So promising low-cost manufacturing approaches. So we got a couple of options there. You can either build this thing in space or you can build it on the ground. Either way, you're going to need to be able to do it in a very low-cost, mass-producible type way that is not really how we build things in space today. But if you could build such a structure like this in space, think how big, how you could make it as large as you needed to. You could build it with robots. All of this feeds together into a concept that once you have some of these logistical capabilities in space, you'll be able to deliver these and build these game-changing technical achievements like the solar power beaming project. Now, if you're going to launch all this mass to orbit, you need to make sure that that part of it is affordable as well. And the cost per kilogram to get into orbit is a big deal. Thank goodness, SpaceX has lowered the cost of launch by a factor of 10 already. And we've got 137 other launch startups out there working to innovate in the launch business and get the cost of launch down even more. That is super enabling because it really lowers the barrier to entry for technical innovators to get their science and their technology up into space. And that is a key enabler of this concept too, since we're going to be launching thousands and thousands of pounds of material just to make one satellite work. So the cost per kilogram to orbit is hugely enabling. And then the last thing is just the module idea that I already showed you, but just that is a potential game-changing technology in itself, in that, you know, you don't have to think of the satellite as a separate thing that collects energy, brings it to a central point, and then beams it out. Instead, every sandwich module does that on its own in a distributed fashion, so that you don't have to bring it all together into one point. That was kind of one of the key breakthroughs of this sandwich module, that makes it totally scalable up to whatever level that you want. So again, those are some of the key technologies that had to come together to make it possible. Been many people that have worked on this over the years. Most recently, you know, the Navy Research Lab, our brothers and sisters over there, recently flew a version of this module on the X-37 space plane. And there have been other demonstrations over the years on various pieces of this that have gotten us to where we are today. So it isn't like this is just a brand new idea out of the blue. This is building on a lot of technology advances over the years. So we'll move to slide 5, and our overall approach to this, again, was to decompose the problem into smaller bite-sized problems of an iterative, integrated, you know, demo type things as we go. But we don't want to do them slowly. We still want to do rapid demonstration-driven projects. So we started out by identifying the critical technology elements and then started parallel tech development paths in each of those areas. We ended up with what we call 2 major thrusts or objectives for going after this. First of all, pull all that technology into the right number of integrated demonstrations along the way, so that you don't have to bring 10 miracles together at the end. Instead, you can bring a couple of miracles at a time as you incrementally build towards the end. That's what we call the integrated demonstrations. But in parallel to all that, continue the incremental improvements in each of the key technology areas. That's what we call the CTE technology development, you know, in the research line up there, number 2. And those are the 5 key research areas where you can continue, if you can continue to make improvements in each of those areas and spiral them into the end solar power beaming capability, you're going to end up with a much better solution than if you just snap a chalk line and say, nope, that is the only thermal capability I'm ever going to mature. Instead, we have a concept of continuing to mature each of those things so that we can continue to spiral them out into the end capability. So those are the two major thrusts. You build the integrated demos, but you keep maturing the core technologies as you go. On the next slide, you'll see the spider strategy and what we're trying to get to. The way to look at this is, let's start with what the objective system is. I already told you we wanted to be able to power a forward operating base with 1,000 kilowatts of energy. So to do that, you need about 10,000 square meters of this material up there in space, and that is the fully operational objective system. So there's then the issue of how many of those you would need in your full constellation, and we have all kinds of concepts there, but bare minimum, maybe 8 of these in a MEO type orbit would give you pretty good coverage of most places on the Earth where you might want to beam power. But point being, it isn't just one 10,000 square meter satellite that's the end goal, but at least 8 of those so that you can have some kind of worldwide capability. But don't look there at the objective system and how you and what you're trying to get to there is then that's our full the element of the full constellation. So then we come down one level from that and say, well, what could we do that's a smaller prototype of that objective system? So a single satellite that would be the operational spacecraft satellite, and maybe this is only 1,000 square meters in terms of its size, still very large, but much smaller than the end, 100 times smaller than the end state that we wanted there for the full-scale spacecraft. But this would certainly be able to beam meaningful amounts of power and prove out all the key technologies. So that's what we call the prototype of the operational spacecraft. That's the second line down there. Even that is not something you would want to build up all at once. Instead, it makes sense to us that you would have a proof of principle prototype, which is the third line down there, which is then a subscale integrated demonstration. And so maybe that's 100 square meters in terms of its size, still able to mature and demonstrate maturity of the technology. And then and in terms of getting to the overall system, we would call that a TRL-7. And then before you get to that is what we're doing right now. SPIDER is the component proof of principle prototypes. Demonstrate each of the components, from the sandwich module to the deployable structures to the actual metrology of how you're going to know where each piece of each element of the structure is. All of those are some of the key technologies that'll be demonstrated as the proof of principle prototypes down there in the fourth line on this slide. So that's how you get each of the component TRLs up in its technology readiness level to where it would make sense to build the 100 square meter integrated system. So when we first got this project a year ago, we did a tech assessment and we're like, okay, this is at technology readiness level 2. We got some work to do, all right? And there's no doubt about it. Super great game-changing capability that's potentially there, but a ton of technology work to do. And that's what we're here to do at AFRL. I mean, that's what we love. I mean, how do we mature really useful and impactful technology? And that's what we set out to do. So from 2 to 9, here's how you get there. And this is where we are right now. We're at that very first level where we're going from 2 up to the 4 to 7 range for the component TRLs. But it's important to know where the end state is so that you make sure you don't do anything along the way that would preclude you going to the end state. So that's why we laid the strategy out like this. On slide 7, it talks a little bit more about the strategy and then how you get from the basic sandwich module again to the overall what we call the Scorpion spacecraft, which is a bunch of those panels put together, and then how you get to powering a forward operating base as the end state there. So again, there's been a lot of analysis that goes into, hey, how much power do you need? And you guys are probably the experts on that as our future energy experts. But I would, the first question I often get when we brief people about SPIDER is, well, what's the efficiency of your system? And the efficiency is darn low. We will tell you that right now, at least for now. But that is not the most important thing. From a military perspective, we think the most important thing right now is to be able to beam this power on demand wherever we want it. So if you will need to beam it to a moving airplane, you need to beam it to a moving vehicle. Those are things that it is not a question of efficiency. It's a question of whether you can actually do it and how quickly you can do it. So we're going to start with that. But I would argue that after we get to that point where we can deliver the power on demand and you have this kind of mass production of these things, the costs will plummet, and you will be able to get and make this an actual feasible energy source that will be cost effective and competitive with other sources of energy on the ground. So I think the end vision of this being an actual, energy source that would replace, other terrestrial energy sources, such, coal, natural gas, those type of things is there. But that's kind of the end state. And on the way there, we think this power on demand feature is going to be very interesting and will help enable that end state. So that was those were some of our thinking that was pretty important to getting to, what is our vision? Is our vision to deliver power as cheaply as possible? Maybe someday, but for now, our vision is to deliver power on demand. So if you move to slide 8, you'll see a little bit more on what the SPIDER objectives are. And again, we talked about how we have 2 lines of effort. One is the integrated demonstrations, and the second one is maturing the critical technology elements. And so each of the demonstrations meant to, again, build on each other and eventually lead us up to maturing the technology readiness level of the end state. All right, next. That is a little bit of about the SPIDER project, and we're super excited about the technology there and where it's going. I guess my overall assessment of it for you would be, yes, this is something that is a great potential future energy contributor, something to watch, but it's a long ways to go. All right, and that's why we need to get started, and we love working on that kind of technology. But to get from here to delivering actual useful energy from space is probably about 10 years away, and at the most optimistic, and that's okay. That's a good reason to go work on it, but it isn't something that's going to solve our problems immediately tomorrow. So let me move on to a second topic that I wanted to talk to you about today, and this is just what digging down a little bit deeper into the technology. If you go to the next slide, this talks about what we're doing for space with the space solar cells themselves. So when you talk about a 10,000 square meter array, you're talking about having a lot of solar cells on there. And so what we quickly discovered is that the effectiveness of this system and even the viability of this system is super sensitive to the cost of your solar cells. And the cost of your solar cells is super closely correlated to the producibility of your solar cells. And so we do have, so we then got down into, okay, how can space solar cells today are still kind of a custom product because they're built in small quantities and they have to survive radiation, so you can't use the same solar cells that you have on the ground. There is a lot of potential return on investment from being able to dramatically reduce the cost of your solar cells. And so that's what this is all about. This dynamic vapor phase epitaxy is a way that we believe we'll be able to get 100 times faster solar cell deposition in the manufacturing process. And again, that all ties into the cost of being able to manufacture these things and just the pure quantity that are going to have to be manufactured to fuel this kind of space capabilities. On top of, by the way, all the proliferated low Earth orbit constellations that have their own solar cells and their own needs and thousands of satellites that they're building. So I think we assess that the demand for space solar cells is going to just dramatically skyrocket over the next decade from all of these different demand signals. So this kind of technology that lowers the cost of them and increases the manufacturability will help not only with the solar power beaming project, the SPIDER that I briefed you about, but with all of these other space applications as well. And so NREL invented this using Department of Energy funded energy funding. They've got a 2-chamber system with state-of-the-art gas technology to produce the substrates that we need. It's a lot like building a microelectronics circuit, as you can imagine. But some of the pictures are shown there in the lower right, where you can actually make these little pieces flexible and very low cost and mass producible. And so that's the overall goal of our project, and we are funding some efforts to show that this is actually going to be achievable, and then have a pilot production system by July of next year. So I included this just as a highlight of some of the work on one piece of the spider system, but it's a critically important piece to get after the cost of the solar cells, so that again, that's an enabler to the overall capability that we are looking for from the spider system. Our first spider satellite we envision launching in 2023. That's the 2 square meter demonstrator satellite. And that's when we will first be able to show the basic technologies of the sandwich module, be able to beam a tiny bit of power to the ground. I teased the program manager that better be able to light up at least one LED light bulb with that sandwich module, so that we can show that the system is working. And I think he knows I'm joking, but we do, with that technology demonstrator, we'll be able to prove the basic power beaming technology. And then from there, just a matter of scaling and logistics and getting the right architecture deployed up into space. That will then lead us to the power on demand capability that we think is so attractive to the military. And then once we have that, that could lead us to actually commercially viable power delivery from space, and could finally be able to realize that vision that, again, been laid out by other visionaries decades before the technology was ready. We think the technology is now ready, and we're eager to get after these demonstrations to prove it. So from an AFRL perspective, this is the kind of project I love. It's the kind of project that has super potential game-changing impact, no doubt, but it's a kind of project that has a lot of challenges along the way, because we love solving problems, and we love being able to demonstrate things that people don't think can be done, that actually can be done if you decompose them into enough problems. And that's how I think about Spider. So this is a great project for AFRL, and we are happy to be off executing it. And I hope that you guys, as you think about what our future energy options are, will in the long term consider things like this and support things like this, because could be a real game-changing capability, not just for the DoD, but for our nation and for our world in the energy area. So with that, I am happy to answer a few questions if we have time left. I think we do have time left. So if anybody has any questions, I will leave it to Tom to moderate, and happy to share a few more a little more time with you.
Great. Thank you very much, Colonel Felt. Of course, in my mind, it raises a whole bunch of questions. And so I'm happy to take up some of the Q&A time if we can, just to bother you with these ideas. First of all, I've been a fan of space solar power ever since I attended a lecture. I don't know if you can see this because I have a virtual background, but the High Frontier, Gerard O'Neill, MIT professor, 1977 is when he signed this book. So I was
awesome.
American Physical Society member back then, and of course he talked about not only the space solar power, but of course colonies in space, and the idea of using a lot of soil and earth to protect us from cosmic rays in a circular type of cylindrical space colony. So who knows if his vision will ever be realized with the human populations in space. But I was pleased to see, I think he was one of the first to actually start to propose and publish on the concept of microwaving down to Earth. And of course, I'm leading up to the question, and that is the biggest criticism that followed him for years was, you're going to fry the cattle that are on the ground and people nearby, and especially now that you I think bothered us significantly with beaming toward vehicles with humans in them. What is your response to the problem of microwave cooking whoever is in the beam?
So I have a couple of my experts here, and they can give you maybe some of the safety discussions that have gone on. so
Okay.
far, but I really appreciate that reference back to 1977 because I wasn't sure exactly when the idea first, was identified as potentially feasible. And I'll go back and I'll check on that article that you pointed out. I think that's great that you have it right there, and we will go chase that down. So again, wow, isn't that amazing that somebody in 1977 had the vision, and here we are finally with the technology to be able to go build this. So and to your point, we have so many commercial companies that are looking to do commerce in space now, and asteroid mining, and human habitats, and habitats on the moon, and all these kind of things. All of those type of things they'll all benefit from this kind of technology. And so, I think this is pretty foundational to a lot of those visions of what the future of space is going to look like, and very enabling concept. The one thing I wanted to say that might have changed since 1977 is that now when we think about beaming it to an airplane or a vehicle, I don't think there is going to be a human in that airplane or vehicle, at least, at least from the military perspective. We've just gotten things so automated that, the UAVs and the unmanned ground vehicles are not as worried about the microwave levels as maybe we were in the past, when you definitely had to have a human there. But I think that's something we got to look at and pay attention to, and make sure that we don't unintentionally create another hazard as we solve the energy problem. Do you guys know anything more about the actual energy levels that we're talking about?
Well, yeah, so we're obviously tracking those, and that's something that we look towards the future at solving. But the size of the aperture will dictate our flexibility and how we can tune in the power density. And absolutely, there are thresholds, safe thresholds. So all that is in the future thoughts. We're tracking it. But like you said, sir, when you held up the tile, our goal is to get to that meter threshold. And those kinds of problems, we'll solve those later, but on the foundation of first proving out this technology and this PRAM module.
Yes, that's a really good point, that we can control the energy density. I mean, that's one of the factors as you trade the size of the aperture in space versus the size of the aperture on the ground. You can dial into whatever safety factor you want in terms of the microwave energy. So yeah, that's a really good point.
Sure, spreading the beam out would lower the energy density. Yeah,
exactly. Yeah.
The other concern I have, though, is the upper atmosphere density. Even if you're spreading it out on the ground, you're talking, what is it, 10,000 feet, 20,000 feet up in the air. What about all you said 8, I forgot how many different installations you wanted to have around the world, but eventually you're going to have the no-fly zones basically underneath every one of them, right? For commercial airlines.
That could be the case. Again, I think that needs to be looked at as we mature the concept for the system. And again, I don't think we have all the answers there, but I think that's something that we need to keep in mind. Now, of course, the beauty of power beaming is that it can go through clouds and it can go through the atmosphere when solar power can't. And by the way, you can beam the power to the dark side of the Earth, from the light side of the Earth if you have your satellites positioned properly. So it's a huge step up over just capturing solar energy in terms of the availability of the power and where you can put it and the density of the power that you're able to deliver. But in the process of all that, you got to pay attention to where the beams are going and all those safety factors that you identify. I actually think that'll be fun to work through what all the COAs are to try to solve those, and what levers you can play with to try to make sure that those don't become showstoppers for the technology.
Sure. Another point that you just mentioned, which I think would be a great sales point for one of your slides, is not only the 24-hour availability of the energy, which really overcomes all of the objections to implementing solar panels on Earth, but also the solar panels in space. I remember vaguely that it's at least 10 times the efficiency, just because the energy density from the sun is not being attenuated by the atmosphere. So every square meter usually puts out 10 times the amount that you would get on Earth.
That's exactly right, because of course you get the solar energy without any atmospheric attenuation, and that's hugely beneficial. On the other hand, you have to do the conversion to the RF and then beam the RF, so you lose some efficiency there. But overall, the system works out to be pretty favorable in a lot of use cases. So that's what's exciting. Yeah.
Starting. In fact, Google is telling me that the International Space Station is reaching up to around 34% efficiency. That most commercial ones on Earth is 15 to 20. Just because
right. Well, on Earth, they're just going for the lowest cost per kilowatt hour, right? So, but in space, yeah, we routinely are at 34% now or so on solar cells, and because it's worthwhile to pay a little more to get higher efficiency when you've got all those launch costs, and you want to be sure that it lasts a long time in the space environment. So, those are some of the differences that we have to pay attention to.
Because I think you were talking about low efficiency panels you were putting up there, but 34% is pretty high. So you've got another sales pitch there too. So, but in general, it can probably impact if this becomes something that becomes a spin-off for commercial implementation by utilities, for example. If we envision several decades in the future and you're successful with the military installation, wouldn't it be possible that utilities could advantageously start to have a percentage of power for each utility, major utility, from space solar power?
Well, that's exactly the vision. Yes, that's what we hope will happen. And, just there's a lot of money too that goes into the distribution architecture for power that's created terrestrially. That needs to go into the equation too. So it isn't just a matter of what's the incremental cost of producing a kilowatt hour of energy, but what is the whole infrastructure cost? Because yes, there's cost to this space infrastructure, but there's also a very high cost to the ground, to the terrestrial infrastructure that's in place now. So if you look at a clean sheet design of energy in 40 years or something, I think you come to some much different ideas than what we have today.
That's a good point. We do actually have a few chat questions too. I think one question was LEO solar radiance provides about 1,300 watts per meter. So about a kilowatt per meter, which is pretty significant. And so you've got an advantage, I guess, from this point of view. And I guess there's also a question about whether this becomes a terrorist target. I'm not sure if that ever, I know the Space Force is a question I can ask about. According to Joanne, I can bring that subject up. And
we love talking about the Space Force. So.
I wondered, now that you have a Netflix competition showing us what's really happening inside with Steve Carell. But no, I'm trying to be serious about it. Is there a concern defensively that such an installation, an expensive installation, could be a terrorist target?
Yes, absolutely. So, but let me tell you what changed my mind that this was actually worth pursuing. So everything we're doing at AFRL now, since the National Defense Strategy of 2018, has been focused on increasing the resiliency of our space capabilities, because we've got the best space capabilities in the world, but they're very vulnerable, and our enemies know that, and that's a potential problem. So these are the words of General Raymond, the Chief of Space Operations. So he has directed us a couple years ago to go all out on increasing the resiliency of our space capabilities to make sure that they're there when our nation needs them the most, which would be in a peer conflict, and by having that kind of a capability to deter a war in space. So those are the main strategic goal of the Space Force and the technology on which I'm working at Air Force Research Lab. So with that in mind, one of the major thrust areas has been to build proliferated constellations rather than huge big juicy targets in space, as General Hayden calls them. And so rather than building $1 billion satellite, much better to have 1,000 satellites in low Earth orbit that can be distributed, so that if you lose one or two of them, you still have the capability. So all of that is all about resiliency, and that's been a major focus area of ours in the lab and in the Space Force. So then, somebody comes along with a concept for, I'd like 10,000 square meters of these up in space, and wouldn't that be an awesome capability? And of course, that is the first thing that came to my mind. It's like, oh my gosh, I'm supposed to be building small sats, not big sats. But you know, but then what really can change my mind about it was that this is a very distributed system. So what I mean by that is that, you know, this panel does not depend on the panel next to it in order to provide effective capability. So for example, if, you know, someone pokes a hole in this panel with an anti-satellite weapon or a laser or something like that, this panel right next to it's still working. All right. And so that was what really convinced my mind, changed my mind about that this was actually a resiliency enhancer, not a resiliency problem, because it's such a distributed architecture, and the 10,000 meters, you know, is very resilient against various pieces of it breaking and falling apart, which is good because that happens for natural reasons too, not just because of enemy ASAT missiles. So all that resiliency is a problem whether you have an enemy attack or not. But that's the really thought process that changed my mind, that yes, this actually was a good idea.
And you're going to be tracking, and you're going to be tracking all the space debris as well to prevent any interaction with the.
Well, so that's also an important consideration, because if you have a 10,000 square meter object up there, it's going to be like a big net to catch all the space debris that's potentially in its path. But that's one of the benefits of being at MEO. There's less debris up at middle Earth orbit as compared to low Earth orbit. And again, I would go back to where if you poke some holes in this thing, it doesn't break it. You know, it's just ever so slight degradation in capability. So yes, those are all the kind of things that we need to be thinking about as we talk about these systems.
Another question that came up in the chat is, this person noticed that you're using gallium arsenide for your solar cells, and he used to work in selenium telluride department. Selenium was used in solar cells on Earth. Does selenium solar cells work in space?
Do selenium solar cells work in space? I do not know. All right, I'm told that they do, but we haven't chosen to use them, and we don't know why, but I think that's a good thing to explore.
See if they're as durable or so forth.
Yeah, I mean, you know, we should certainly put them through the test chambers and see what the capability is if they're lower cost. I mean, again, these concepts are super sensitive to cost now, so I think that's worth looking at. I appreciate the technology tip.
Another question is there any technique to avoid the 1/r² power transmission loss? And where R is the distance between the RF transmitter and the RF receiver?
I'm not aware of any way to defeat the laws of physics, no.
I think that's what the question is. Yeah. Another question about Jaffe and the Navy have flown an SSP test article. Professor George Sowers at Colorado School of Mines is another person that apparently has investigated this. I don't know if you're
Yes, in fact, I mentioned the Navy Research Lab test article that was on the X-37 during my talk there. They just recently flew that. There have been previous modules like this on the International Space Station. So there have been a few little demonstrations that, again, have led us to think that, yes, we are finally to the point where this technology is feasible.
Okay. I've also got a personal inquiry. I'm sharing a screen of the IEEE spectrum. I'm a member of IEEE Electroengineering Institute. And here's a story from a couple of years ago where Japan has been demoing and broadcasting and bragging about their wireless transmission from space solar power. And they even were talking, as they do here, about the 2030s as their target. Even though recently I haven't seen much advance in their achievement toward this goal. But I just wonder what your opinion of this major competition from around the world.
Yeah, again, I think these technologies have been, in the gradual maturing phase for some time. And so this was 2015, it looks like. And yeah, of course, it's good to do demonstrations on the ground on your way to orbit. And that's part of our engineering philosophy as well. So I think this was also one of the baby steps along the way to where we are now in terms of maturing the technology. it isn't like just one person has been working on the technology. It's been, of course, all the researchers all over the world that have been gradually maturing each piece of technology. And I think that's one example right there.
Well, what if I up the ante a bit and say, well, Japan's going to be putting out a gigawatt while you're just doing a megawatt?
I hope they do succeed in putting out a gigawatt.
Come on, JAXA is the researcher that you have to contact and tell them to slow down.
Well, I know. Hey, you know, competition makes us all better, and collaboration can make us all better. So
Sure.
I do think there's lots of opportunities to work together on some of these very big tech challenges, and the benefits of this technology will help all of humankind. So, you know, I applaud all the efforts from other countries to also mature this kind of technology.
I see. So you don't view this as an international political problem?
The only way I view this as an international political problem is if someone corners the market on this stuff. I do worry about a peer competitor cornering the market in this area. But other than that, no, I think there's lots of utility. And as long as we can develop this kind of capabilities for our Air Force and our Space Force, you know, I think we'll be okay. I just wouldn't want someone else to be the only ones with this capability.
Sure. When I grew up, I used to buy things that said made in Japan. I'm just wondering if this is going to happen again with space solar power debris.
I wonder that too. Very, very seriously, I think that there are huge opportunities. This is one example of the huge commercial opportunities in space. Yeah. And I really want to enable our US companies to be able, and our allied, and our partners and allies to be able to be successful in this area. That's one of our main goals of our industrial policy in space, and one of the main reasons that we try to have such close partnerships with all the commercial, you know, adventures and ventures in this area. Again, they're spending 80% of the money. So what I'm trying to do in Air Force Research Lab is, you know, leverage what they're doing, shape a little bit of what they're doing so that it can be helpful to us if they haven't thought of some things. Those are the kind of things that I think are the opportunities there. And we really want to help those companies be successful in their ventures and adventures, as I accidentally said, but that is part of it too.
Even if they are foreign countries, in other words.
Well, partners and allies certainly, and again, you know, my main concern with our peer competitor foreign countries is just I don't want them to corner the market on these kind of things. That could be strategically very bad for the U.S. So, you know, to the extent that their efforts help mankind and humankind, wonderful. We would like to collaborate at that point. Mm-hmm. But I also don't want them to have a military advantage that we don't have in this nation.
I see. So, and you're not really sharing with us very much about the military strategic goals for obvious reasons, but the technological goals seem to be very universally useful for the commercial market as well as for the military market.
Well, I'm not trying to hide the military applications. I just think you can. I just think it's pretty easy to envision the ways that many platforms could benefit from having power on demand. I mean, just think about an unmanned air vehicle that never had to land because it could have you could be beaming power to it all the time.
They're doing that already with solar panels on the wings.
Yes. So that, and you know, ground vehicles that you don't have to haul fuel across, you know, IED-ridden roads in Afghanistan to get to the forward operating bases. You know, I think maybe I should create a slide on some of the military benefit ideas, but it doesn't take a whole bunch of imagination. Everything runs on energy, right? So any way you can get energy on demand, it helps across the whole spectrum of military operations. But I think that's a good point. I mean, we could illustrate that a little bit more clearly, but I just gave you some examples of what we're thinking.
Yeah, and also the higher efficiency in space. One question that just popped up is about the political viewing of other countries seeing this maybe immaturely viewing this as a space-based directed energy weapon. which, you know, it's possible, I guess.
I think, you know, you don't, any technology could be a weapon, right? So that is not our intent in developing this technology, but, you know, it could potentially be used in that way, I suppose, as most technologies could.
And do you see this powering spacecraft as well?
I do think there are interesting applications in beaming power to other spacecraft. Yes, that is one of our use cases.
So maybe you'll help us get to Mars after all.
Could be.
Have the conversion. I don't know if the microwaves through space are any more efficient than sunlight, but
yeah, someone would have to take a look at that. I'm not, you know,
well, you'd be concentrating.
The power density could be a little higher, but whether that's an advantage or not, you know, I don't know. Someone could look at that.
Yeah, laser beam toward the spacecraft. So, okay, well, obviously I could keep asking questions all night, but any last words about the Space Force that we need to know as we view the Netflix satire?
Well, we do laugh a lot at the Netflix version of Space Force, but on a very serious note, again, I think the stand-up of the Space Force has really focused our nation's and our DoD's attention on how important our space assets are and how vulnerable they are, and the importance of developing a culture and doctrine for war fighting in the space domain in case we ever have to. And that's been the biggest, you know, revelation since we stood it up, since the Space Force stood up, was just the importance of maturing the thinking of how you would do warfighting in space if you ever have to. The Space Force just released their seminal doctrine publication earlier this week. If you haven't seen that, it describes how they envision having to do all these operations in space, these warfighting operations in this warfighting domain. It lays all of that out there. And the pace of thinking and maturing of the doctrine and the tactics, if you will, for how to do this has really accelerated since we stood up the Space Force in a good way, and lots of good thinking going into that. And the reason that's so important is that you know, if you want to deter your adversary from ever taking any action to deny your space capabilities, then you need to show them and convince them that they're not going to gain a military benefit from doing that. And that's exactly what the Space Force is aimed at doing, is if we can deter that kind of conflict by thinking through it ourselves ahead of time and developing some key technologies ahead of time, having more resilient systems ahead of time. That's been the real benefit of standing up the Space Force so far, and just getting started. So it's exciting to be a part of that.
Oh, I see. So it's really not, as they portray it, a competition to the Air Force, which already has a space division.
Not as competition to the Air Force at all. I mean, it's actually, the idea being is let's have, you know, the Air Force gave birth to this new service, the Space Force, and is really committed to its success, not to competing with it.
I see. No competition. Okay, well, that's good to know. Well, I really appreciate your taking the time out to address us, and this recording will be available on the website and I think on our YouTube channel as well. But futureenergy.org is our website, and we're wishing you all the success in your future endeavors.
Thank you very much. Really appreciate this opportunity to talk to these energy enthusiasts we have here on the line. Have a great weekend.